Okay, thank you, Julia. Even if she's not online, I think it's a very interesting talk. So we go to the next talk from Hans Hersbach from the ERA community from ECMWF.
Good morning. Can you hear me? Thank you for inviting me. Do it myself, isn't it? Is that just this one? This one? Hello? Oh, okay. Oh, okay. I was going. Ah, yeah. Okay. Yeah. Okay. So overview of my talk is I will say a little bit about the ERA5 reanalysis, what it's about, and where we are. Then I show you where the ERA5 reanalysis sits within the suite of reanalysis that ECMWF has produced over the last few decades. Then planning of ERA6. On special request, I will say something about ERA5 strengths and weaknesses, and I try to focus on the ocean and some concluding remarks. Okay. I don't think this is working very well. Oh yeah, there it is. So ECMWF operates the Copernicus Climate Change Service and also the Copernicus Atmospheric Monitoring Service comes on behalf of the European Commission. And one of our central gateway to the general public is our climate data store. Actually, we are merging it now with the atmospheric data store called the Climate and Atmosphere Data Store. So a lot of data sets there. We have things about observations. So talking about the past, the present, and our possible futures. And reanalysis is an important. Reanalysis is an important component there. I don't think this works. So that's where we are. So I'm going to talk about that. So the status of ERA5 global reanalysis. So it's a full observing system, global reanalysis. So Laura talked about CERA20C version 3. So they restrict the observations to surface pressure, and we take anything we can get. So and we describe the atmosphere, the land surface, and the ocean waves. So not the ocean, but we do have the ocean waves. It's a very popular data set. We have now over 132,000 users, about 100 new users every day. They download more than 700 terabytes per week. And also there's a lot of different users from all different for all different needs. Of course, there's also a lot of scientific users. And for instance, the ERA5 journal paper has already more than 10,000 citations. So that's really, really successful. So it's produced from 1940 onwards. And every day we add another day, 5 days behind real time. Then it provides hourly snapshots at 31-kilometer resolution, up to about 80-kilometer height. And also important, I will talk about it later, there is an uncertainty estimate from a 10-member somewhat halved resolution. Then we also have a downscaled product with only land, not ocean, land, at 9 kilometers. And that's available from 1950, also 5 days behind real time. So the total data set is about 12 petabytes. We use all the observations. We use well over 100 billion so far. But we also need some external data sets like SST and sea ice cover, but also for the radiative forcing, greenhouse gases, aerosols, total solar irradiance, and also ozone. We have a prognostic ozone model in ERA5, but in radiation we still use a prescribed diagnostic ozone. In ERA6 that will change. Okay, so what is the accuracy of ERA5 over the years? Because the observing system has changed dramatically, isn't it? So that's shown on the right-hand plot. So you can see there so this is something we always do at ECMWF because it's in our DNA. We always have forecast, medium range forecast, ECMWF. So for ERA5, we also produce 10-day forecast from the ERA5 reanalysis, and then we look how well that then verify against the reanalysis at verification dates a few days later, and that's actually we find that it's quite an accurate measure of how accurate your reanalysis is, because better analysis produce better forecast. The conversion is not always true, but it works really well. So you see here the evolution for the different products that we have, 1940 to 5 days ago, and this is now over Europe. Basically the measure is with respect to there's some measure there, and 95%. The number of days that you have an excellent forecast, which is this measure, normally correlation coefficients higher than 95%, a good forecast 80%, and a borderline forecast. And you see that increases over time because we have more and more observations. You also see that if you look at other reanalysis that we have produced in the past, starting with ERA15. That every time when we had a new reanalysis, we got a boost in the forecast skills, so our products improve. So so ERA5 is the best of all of them, and ERA5 is also the one that has the longest time series of all of them. You do see though that before 1960-ish, 1958, that the scale goes down quite a bit because the observing system get much less dense, so much less observations. And this is not for the Europe and the Northern Hemisphere, things still look good. But over the Southern Hemisphere, these scores really drop really dramatically before 1979 already, because that's where the satellite era starts about 1979. There's also satellite data before, but it's much less sparse. Okay, so but still, right in the beginning, 1941. ERA5 is doing quite a good job in representing this storm, which was a really intense storm over the Iberian Island. And you see in red the observations that we used to produce that analysis. So it's not that many, but still we are able to get a very good analysis. And and if you look at the ensemble spread, which I will show my next slide, then this typical ensemble spread is still much smaller than natural variability. So we still have confidence that this is reasonably well represented. So basically the message in the Northern Hemisphere, you go back to 1940, synoptic variability is still okay. But when you go higher up the atmosphere, then all kind of systematic errors start to bump up because they don't have observations there anymore. And on the Southern Hemisphere, we don't really have many observations, and that synoptic accuracy is really lost. But of course, you have the model climatology, which is also very useful to have that. So, okay, let's go to the next one. Next one, yeah. So about the synoptic accuracy versus climatology. So what I show here in the top left is the variability for, I've done it for several, we can do it for any type of parameter, any level, because that's all in the CDS, you can just download it yourself. So it's very quick because it's all regridded and it's on disk, so it doesn't take much to produce this kind of plots, much time. So this is the synoptic variability for surface pressure. There's just a variability, just look, and I took out the seasonal cycle and also the daily cycle. For pressure, not so important. For temperature, of course, it is. And there you see that, as you expect, in the tropics, surface pressure doesn't really vary much. But in the exotropics, it does a lot, especially in storm tracks. So, and that's a kind of the benchmark. If we then look at the typical ensemble spread for surface pressure from 1940 to 1949, then you see that on the Southern Hemisphere, I already mentioned, the ensemble spread is almost very similar to the the synoptic variability. Basically, you don't have scale there, synoptic scale. But if you look at the northern hemisphere, then you see there is, because this ensemble spread is about a factor 10 smaller than the variability, especially where you have the most observations, which is in the US and in Europe. Now, if you go further in time, so when you are now starting in the satellite era in the 1980s, then everything has become much more improved. So southern hemisphere as well, although the northern hemisphere is still the best, because we also have a lot of in-situ observations. Radiosondes are very important. And then when you look at the most recent 10 years, then of course everything is much better again. And still you see that where you have the most in-situ observations, that's where you have the lowest spread, so the highest confidence in your products. Okay, so well, ERA 5 is not the first reanalysis I've produced, as we have done many types of reanalysis. So also for quite a different components. So we started with atmospheric reanalysis, and then later land components were added, and also ocean waves. So I'm not going into detail in which all the different reanalysis we have, but we are now here at ERA 5. Then we have also done a number of ocean reanalysis, and actually there's even ocean reanalysis done before this, but we were not really named as ERA-S1. That's also started quite a long time ago, and we have now ERA-S5, which is used also in our NWP system to provide initial conditions for the service for the 10-day forecast. Then we have also centennial reanalysis, like the 20CR version 2 and 3, which Laura talked about. They were more in a research mode. So we had ERA 20C, Sierra 20C, which was actually coupled with the ocean, but centennial really coupled with the ocean. Then we have dedicated land reanalysis. Then mainly they are downscaling of the atmospheric reanalysis, so no new observations are added, but we're going to change that in the future. And then we also have reanalysis for atmospheric composition. Okay, and of course in the long term we want to couple everything. So where are we going next? So ERA 6. So ERA 6 will be coupled with the ocean, but it will be a one-way coupling. So we will get our ocean conditions from the next ocean reanalysis, which is ERA-S6, Ocean 6, which Eric talked about yesterday, I think. Yeah. Then we have an ERA 6 land component where we will also assimilate observations. And there will be next also next atmosphere composition reanalysis. Okay. Just yeah. So okay, so ERA 6. So the resolution is I can change the slide later and put the resolution there. We are doing a lot of tests with different resolutions. ERA 5 resolution is 31 kilometers. We're testing with either 18 kilometers or 14 kilometers. So both are looking good, but it depends a little bit what we can afford, the amount of computing units we have, because we need to also our products are much more extensive than a normal NWP output, and that also comes with a cost. So we're all testing things at the moment. We don't know yet. It's either going to be 14 kilometers or 18 kilometers. Okay, so we need to do a lot of work there, of course. All kind of science has to be done and innovations. So there are innovations which are really dedicated to reanalysis, which don't really work out of the box in our latest NWP cycle, because of course a reanalysis is based on a recent NWP cycle. So first of all, we need to establish the coupling for the forthcoming ERA-S6 and Ocean 6 ocean reanalysis. So we're testing it now. So there's different options. Maybe I've done too much time to go into the details, but one of the things we're testing now is to try to really, we have this 40 VAR system with outer loops and short forecasts. We want to couple the NEMO 4 model that we use in the ICE model already in those trajectories, getting the initial conditions from ERA-S6, but then in the data assimilation, we don't do ocean assimilation. So we do get all the ocean information from ERA-S6, and we use it consistently in these outer loops, but we don't use it in the data assimilation. So that's what we're thinking about now, what we are testing. So there are all kind of things. Systematic model error. Laura also did this mentioned that mainly we're stressing that now in the stratosphere. So we are improving on that. We're using a method called reconstraint 4D-VAR, which is in our operational system, but it requires anchor observations that you can trust without having to do bias correction. But you go further back in time, you don't have so many of those anymore. So we are developing how we can do that. And we are now working on a neural network in which you can predict the systematic model error, and the training set is a recent period in which we have all these anchors available. We need to also improve on the evolution of the uncertainty estimate, and we also want to address known issues where possible for ERA 5. Then, of course, we make use of the latest ECMWF mature R&D. So ERA 6 will get an additional 8 years compared to ERA 5. And this is just a selection of recent developments. So we had quite some problems with snow in ERA 5. We had a jump in snow in the mean state of snow in 2004, when we started to use IMS data. And also in mountainous areas, we have too many snow. So we're working on that to improve that. There is ERA 5, the ocean waves, extreme waves are not high enough, or they get way too high. So that's due to the drag at extreme cases. So that will be improved. Ozone, we improved the ozone model, and it will now also be in the reagent scheme. It will be prognostic rather than diagnostics. We had recently a revision of moist physics that should have a positive impact on clouds, precipitation, and radiation, and therefore improve on systematic model biases that we have also over the oceans. And that's important for for the radiative forcing, for that also goes into the ocean. Vegetation cover and type that we will change, and we will also use a new set of aerosols and greenhouse gases, which we will also evolve over time, as we did in ERA 5. Okay, so Laura already touched on this. What is the same figure actually she showed? What is the impact, one of the added values of having an ocean involved? So this is an example of ERA 20C, which was not coupled with the ocean. And on the right-hand side, you see a Hofmüller diagram of tropical instability waves based on the SST product was ingested, HDSA2, and you don't really see any tropical instability waves because this HDSA2 product has a temporal resolution of a month, just smears them out. But then if you do the coupling, which is in ERA 20C, then the ocean model does know about tropical instability waves and it recreates them. I'm not saying that it does it correctly always synoptically on the right place, but actually it generates it, and that looks physically much more realistic. So that is an example of added value of having a coupling with the ocean. Okay, so about ERA 5 strengths and weaknesses. So some strengths, of course, it's a very popular data set. So there's also so a lot of people are using it. So there's a lot of people know about what is good and what is bad about ERA 5. So everything is very well documented, both on our own websites, on C3S websites, or our journal paper. But there's also a lot of literature out there as well. If people ask me, oh, do you know what ERA 5 is doing in this particular application, or this particular phenomenon, I just go to Google Scholar and I type ERA 5 and the subject, and brrrp, you get 5 or 10 or 20 papers that have looked at that. So that's an advantage of a popular product that really many people have looked at it. And it's high resolution, state of the art in 2016, as accurate as possible. We have this uncertainty estimate. I think it was really important to use that. Yeah, and it's easy access, and there's user support. So if you have questions, we look at your problems, and we try to help you as good as we can. So some weaknesses, and then relating to ocean forcing. So there's a more complete list here in this website. Okay, I already mentioned that before 1979, the synoptic accuracy is low over the southern hemisphere. But I mean, it's still we have we still have the model there, so it doesn't mean that you couldn't. It depends on your application, whether you can still use. If you need synoptic accuracy, then you have a problem. But if you don't really need it, and more climate and climate variability, then you should still be. But more or less okay. We have occasionally very strong winds, up to 300 meters per second at isolated locations. So that blew up our ocean model, for instance, when people are doing tests. But we have documented a solution in our on our website. It's very occasional. Then there's some small systematic jumps at 10-meter wind across the ERA5 data simulation windows at 9 and 21 UTC. We have some systematic biases at some locations in radiation, but in ERA6 hopefully that's improved. And we have some local issues with sea ice cover and SST. Okay, so my final slide, if I had 30 seconds. Yeah, so ERA5 produced hourly snapshot over 83 years. Okay, upper air temperature, low frequency variability looks reliable, downwards to 10 hectopascal. From mid-1940s onwards, humidity and ozone is more challenging. We are preparing for ERA6, so already went through all these points. Then we're also looking ahead. We're also already thinking about ERA7, where we want to have a fully coupled with the ocean, and that's really research. And we do that very strongly together with the research department, because that's what they want to do as well. And we also have funding from all kind of external funding from a number of European projects. And then finally, we receive a lot of feedback from our users, and we listen to them. So we're user driven. So if you have any, requirements, I'm not going to promise that we can, incorporate them, but we do listen to you. Well, thank you so very much.
Thank you, Hans. There is no question on Slido, but we have time for a very quick question on the room.
Thanks very much for the presentation. So I will ask a question rather than go to Google Scholar to ask it. But one question on this, also in comparison with the previous talk. So you explained that you take all observations that are available for the ERA5 that we know very much. Still, I mean, this is also part of the Copernicus Climate Change Service. So, I mean, ERA5 is also one product for climate monitoring. So can you comment on this impact of the evolution of the observing system, which is huge over the duration, on how it's impact the usefulness of ERA5 for climate studies?
Hello. Yeah, that's a very good question, because that's where really reanalysis historically have been struggling a lot, atmospheric reanalysis, just because of that. And then you have the interplay between systematic model bias and an evolving observing network. So systematic model error is basically the prime enemy here. So we try really to improve on that. So we have this reconstraint 40VAR that we use in ERA6. But having said that, in ERA5, I think for 2 meters per temperature, I think when you go below 10 hectopascal, so it's lower troposphere, lower stratosphere and troposphere as a whole, I think ERA5 you can trust very well the low frequency variability and the trends. Before 1945, then when you go higher up in the troposphere, it's less reliable because we don't have radiosonde observations anymore. So that's really, I think that we can really trust, and particularly also with the last 30 years, because then we're already in the satellite era, and when you do climate monitoring, typically people look at anomalies with respect to the official climatology. So the official WMO climatology is now from 1991 up to 2020. So that is really well observed periods, so we don't see much problems there. If you look at other parameters like humidity and ozone, then it's more problematic when you go further back in time. But for this 30-year period, I think it's, does it give a kind of a, and we're also working with our contractors to reprocess observations and to do data rescue, to get as many historical new observations that we can that are still outside there, but haven't been digitized or have been reused again. So we're working on all fronts.
Okay, thank you. I think we have to move up to the next session. And Karina, I'll let you the floor.
Thank you very much. Okay, so welcome to the next session. So we were gonna go now on the reprocessed observation, reprocessed meaning the delayed mode data, and we are starting, we will have 3 different talks, one on the remote sensing data, one on the in-situ observation for physics, and one on the in-situ observation for biogeochemistry. So we start with the physics with Antonio. With satellite, sorry.
Hello. Yes. Okay. Good morning. Good morning to everybody here in the room and online. So my name is Antonio Reppucci. I'm the coordinator of Earth observation data at Mercator Ocean and for the Copernicus Marine Service. And I was kindly asked to provide today an overview of our portfolio based on satellite reprocessed observation. So let's see. Oh, no. Sorry. Okay. Second. Okay. So the Copernicus Marine Service has done a rather strong effort since the beginning to provide marine multi-year products, which for satellite observation are also called REP. These are basically high-quality long data records that can be used for a wide range of application, from general ocean circulation, marine resource to climate change, and are used by all categories of our users. Main objective of this product are, first of all, to support our monitoring and forecasting center with data required for assimilation, validation of boundary condition, but also they are used to monitor and to report on the marine environment from the past to now. They are, of course, an integral part of the service catalog with an effort to provide a continuous description of ocean variables over the past decades, consistently with the real-time production. This is the interim concept that was probably already mentioned during these days. I will provide a bit more detail at the end of my presentation. The particularity of our REP product are that they provide the best info at a given place at a given time, at global and especially resolving mesoscale features. And this is done using all the available satellite information which is provided in the place at the time. So this is make probably the bigger complementarity with the C3S product, which are instead designed to be stable in time and provide a global information. Of course, all our portfolio is developed in coordination with the Copernicus Climate Change Service. We are very regular in consultation, interaction, and going a bit beyond. Thanks to an agreement between ECMWF, Mercator Ocean, and the European Commission, we have started the production of ocean ECV for the C3S service is done by Copernicus Marine Thematic Assembling Center since the beginning of this year. So a quick look to how REP are produced. Basically, we use upstream data for the Copernicus space component. These are the basic satellite L1, L2 data. We take in-situ observation from all available European and international network. And then we have a set of 8 thematic assembling center, which are the responsible of the of processing upstream data. We have 7 of them, 6 of them for each of the ocean variable of relevant for the service, 1 for which aggregate in-situ data, and 1 special thematic assembling center, the multi-obs, which has the particular task of taking as input data from the other TAC and merge them, aggregate them, and to provide added value information. Output from, in general, from all the TAC are aggregated L2 in-situ product or gridded L3 or gridded and interpolated L4 product, which are fit to be then assimilated by monitoring and forecasting center. So we are a Copernicus services, so a service. So of course we make quite extensive use of satellite data. We have taken on board all the Sentinel which are observing the ocean as soon as data were available from the space agency. We are looking already to the future to take on board the future mission, but this is not relevant today. What is more interesting maybe is that we make a very, very huge use of past mission. I try to count them, I end up with 60 or more, but probably I forget some of them. You can see that for the sea surface temperature, more than 20 missions are used, 15 for sea level. And you have to imagine that when came to make the processing of the full data record for sea level, this 15 mission cumulate more than 100 years of observation. So this to provide you an idea of how huge is then the effort to make a full reprocessing. So next slide, I will try to provide you a bit more detail on our catalog. So starting with sea level, here we have the REP product, which is based on the mentioned 15 mission. This is provided at level 3 and level 4, and is available at global scale and Europe. And now is the version still on the catalog, the DT 2021, but next year will be available the new one. The processing is ongoing, and they distribute the C3S product. For SST, okay, the first line is maybe too gray. So I put it in gray because this is a product which is not yet in the catalog. It will be very soon in November. It's our new SST REP product based on the Odyssea processor and processed at Ifremer. Then we have a set of regional products which are produced by the different production centers that belong to this TAC, and they are mainly aiming to provide the best information on each of the basin. And as I said, we redistribute the SSCI C3S climate data record, and also the Ostia, the processed product, is still is in our catalog. These products are updated monthly, but also some of them with a higher frequency, and they are able to reach 1 month before the real time. Ocean waves. Here we have two products. One which provide a data record of the conventional altimeter and is based on the SSCI processing. And the second one that is dedicated to synthetic aperture radar, providing spectral information, period and wave direction, and it's based at the moment on the Sentinel-1 satellite. Winds. I have to say that the WindTAC did quite huge effort in the past couple of years to provide a set of newly renewed products. So we have a REP which is providing at L3 and L4. It's merging information from scatterometer and blended with ERA5, and it goes as a sampling, hourly sampling with a monthly interim. And then they also more recently starting distributing the processing dataset at L4, which contain monthly means. Ocean color. Our ocean color product is the globe color one, produced by Agri, available at level 3, level 4 globally. Then we have again we distribute the SSCI C3S dataset, and we have again a set of regional product which are processed with different algorithms with the objective of providing the best information for each of the basin. And all of them are again updated with there are different frequencies of update depending on the availability of upstream, of course. CIs, the CIs rep portfolio, this was a strategical decision, is mainly based on brokering from ESA CCI, OSISAF. With OSISAF again, it's an institution where we have regular interaction. We provide requirements, and then the product are shaped together. So we have the two of them product that are redistributed. We distribute the CIs and sea surface temperature, which is produced by the MI and available also on C3S. Then, in addition to this, IFREMER is providing CIs drift at low resolution. This is a scatterometer-based product and radiometer. And at regional scale for the Baltic, FMI is providing a set of products with different variables of interest over the basin. We come to the multi-ops, which is quite active, I have to say, to propose the products that are different and covering different variables. We have the well-known Armor 3D, which is based on merging ocean topography and in-situ observation to provide projection along the vertical and provide a different variable. We have the carbon and nutrient information along Argo float, which carry oxygen measurement. The satellite ocean color and Argo algorithm, which also provide particulate ocean carbon, chlorophyll, and backscattering. And we have the global ocean surface carbon product that, again, this is providing information on CO2 fugacity, pressure, pH, and other information. All of these are machine learning based algorithm. Then the MOBTAC also distribute the globe current product, which is basically geostrophic currents based on satellite altimetry and in situ measurement. And the Omega 3D, which in addition to the geostrophic currents also provide vertical velocity. And last but not least, since a few times they are also distributing the ESMOS salinity from the French ground segment, and an additional product, this was the last one added, which merge ESMOS and ESMAP and provide sea surface salinity and density. So I think this ended the list of our thematic assembling center. As I told, just a few words about this concept of interim, which apply probably a bit differently to the thematic assembling center, because they strongly depend on the availability of satellite data. So the ideal case would be, as Marie and the team was explaining, is the idea is to produce multi-year using so the climate data record, and then extend them using the interim production using high quality delay time satellite information. So and going up to 1 month. Today, after many discussion and efforts between our production center, but also commitment from the space agency, this is feasible for ocean color. I just list here the more relevant variable is possible for ocean color. They are doing it. For sea surface temperature is the same. They reach the 1 month, while for the sea level TAC, it's not possible. And this, I mean, I put it as an example because here there is a limitation on the processing to obtain the high quality interim upstream, because sea level, first of all, you need time to obtain precise enough good orbit information to produce your delay time, and then they use an algorithm that make use of a sliding window of several weeks before and after the day of the processing. So this ends up that in ideal case you need 3 months. You cannot go more than 3 months before the real time. And this does not take in account fluctuation that are then due to availability of upstream data, because sometimes satellites are not providing data. There are omission of orbits or incidents. So I think this takes me to the end. Thank you for listening, and I will be happy to answer your question.
Thanks very much, Antonio, for this overview on the remote sensing data. Are there questions? Big question on this? So I have one. So it's a more general one in respect with this discussion we have here. Where do you see, I asked this question in order to identify opportunities, what to do, but in terms of strengthening, or where do you see the biggest challenges at this nexus between the reanalysis and the reprocessed data? What is the major use? What are maybe the opportunities we can improve there? For example, it's because if we use reprocessed data, it goes maybe also to reporting and indicators where we start to put those type of data together.
Yep.
And so maybe it's also dialogue when there are, for example, changes in the reprocessed data, that they are faster communicated. Or,
Yep.
and this can, or is there something
Okay.
else?
This is one point that should be really, we should take care. It's the communication between, because happens that there is a long value chain between the satellite observation and then the use that you make. So probably this we should keep. We are trying to do our best to provide information on what is changing. Not always, but it's not easy always, because changes are happening suddenly. And then, well, for the future, probably we should see approaching the near real time. Also, this is something that where we are trying to improve as much as possible, given also the limitation.
Thank you, Antonio. I was wondering, what's your suggestion for the MFCs that are producing interim every month extending? Do you suggest to keep using the near real-time products for the assimilation for the MFCs who are assimilating sea level anomaly to be consistent with the other data products, or use the reprocessed data, for example, for SST and near real-time for the sea level anomaly?
Yeah, I think that the best will be always to rely on the interim, because they have a kind of upgraded the processing behind. So for sea level, yes, we know there is this limitation of the 3 months. So this, I think.
There's one from the chat. So one question. So it's about, is it possible to have A2 products available for waves? We don't know who this asks, it's anonymous. So L2 products for wave.
No, okay. The marine, so all the Copernicus service, so we are committed to provide L3 and L4 product. L2 product responsibility, production and distribution of our space agency.
Do we have, I'm not so familiar with the older satellite. Do we have any older satellite that we can go back further on? Because
I think that for sea surface temperature, they start with the SSMI, and I think there was something before, but this is, we reached the limit.
Okay.
82, it's already, I mean, it's we are quite going backward.
Thank you.
There are few probably experimental, but the quality of the data were not enough good then to be consistent with all the other.
Okay, thank you very much. Thank you for
You're welcome.
providing us all this information. And so we would move ahead to the next on the in-situ observation for physics by Tim Boyer.
Good morning. I'm Tim Boyer from the NOAA's National Centers for Environmental Information, and I'm here to talk about in-situ physics. So when I first put together the talk, I was basically just going to give an inventory of available in-situ data for reanalyses, and something that we were forced as an observing community to do recently to understand the effects of the pandemic on global ocean, and we published a paper in BAMS recently. But I noticed when looking at the author list here, there are only from 43 authors, there are only 2 that were from the modeling reanalysis community, and which is somewhat striking because the reanalysis community is a major consumer of the observations from the observation community. So I decided to listen over the last few days and see what really the reanalysis community is looking for from the observations, from in-situ observations in the observation community. So, and one is still, I still will give a quick inventory of available in-situ physical and chemical essential ocean variables. I'll focus on observations rather than in-situ derived products. The last talk covered those very nicely. Look at spatial coverage of observations, both recent and look back historically, and look at how we aggregate these observations across the observing systems. And that will be the World Ocean Database I'll talk about, which is what I'm most familiar with, which is subsurface ocean profile data. And then look at fit for purpose in-situ data, and that's the International Quality Controlled Oceanographic Database, which is specifically prepping these in-situ data sets for specific use, reanalysis, and in the case of IQUAD, ocean heat content. And then talk about data delivery, equitable access, direct cloud access. How do you get these in-situ observations? And then look at beyond the ocean profile data, which I'm most comfortable with, that other in-situ data sets that can be used for global and regional reanalysis uses. And then what do we as an observational community actually need from reanalyses? So the inventory, so essential climate variables include the essential ocean variables. This is the World Meteorological Organization's set of essential climate variables, and many of those are ocean variables, and those are governed by the Global Ocean Observing System, which is structured under the Framework for Ocean Observing, and consists of assessment, design, and utilization and dissemination of measurements of relevant essential ocean variables. And the focus here will be on the actual execution, not the design, but the execution of the GOOS, the measurements and the delivery of essential ocean variable data. And so this is from that paper looking at the effects of the pandemic and looking at ocean observing system in April, June, before and during the pandemic. In April, June is a period chosen because in 2020, that's specifically when the pandemic started to affect the observing system. And it's hard to really see any differences year to year in these maps, because especially in the surface, because observation coverage is quite good. The volunteer observing ships take marine met and ocean surface data, and then you have drifting buoys which give ocean current information, surface pressure, and surface temperature. And you also have, it's hard to see here, but a large network of coastal buoys that that give regional information near coast. The subsurface is much sparser, and the backbone is of course Argo. But there are other parts of the observing system, the ship of opportunity with expendable bathythermographs, the CTDs from ships, and research ships mostly, and the tropical moored buoy array, and even instrumented pinnipeds. So there's much beyond Argo, and also ice tethered profilers in the Arctic. And so looking at a little closer at the subsurface temperature observations, specifically, Argo is in the background here in gray. Otherwise, it would be hard to see the rest of the observing system. And this is 2019, just before the pandemic, kind of the height, if you will, of the observing system. And you see that Argo covers the entire global ocean except for marginal seas, where you and the Arctic, where you have ice tethered profilers. You have the merchant ships with the expendable bathythermographs. You have the pinnipids, which cover a great deal of area, which are otherwise sparsely covered, specifically the South Indian Ocean, the tropical moored buoy array, and other ocean sites buoys. And the CTD data here, I'd like to draw your attention. It's not easy to see on the map, but in the Northeast Pacific, these are all data from the International Council for Exploration of the Sea, from research vessels, and you also see around Japan and Canada. And you have gliders, which cover quite a bit of the US coast, Australian, and parts of the Mediterranean. So a lot beyond Argo, although Argo is the backbone, there are a lot of other observations available for reanalysis. And then 2022, as the system starts to recover, you see Argo is still there, of course, and you'll see specifically in the Northeast Atlantic, there are no ship observations. And this is not because those observations were not taken. This is a breakdown in the data flow, in that we in this case, the National Center for Environmental Information did not execute data exchanges during the pandemic and after with ICES. So that data was not passed on. And so I did want to specifically look at repeat hydrography, because this is important. So most of the observations we're talking about are temperature, and a lot of them also have salinity. But repeat hydrography, these are decadal cruises that take deep data, temperature and salinity, but also other variables such as nutrients, oxygen, carbon variables. And during the pandemic, all of these cruises, or most of them, were completely canceled. So we lost basically a decade's worth of observations for a lot of essential ocean variables. But also, the research cruises also are responsible for dropping drifting buoys and Argo floats. So this is the backbone of the system, and it was lost during the pandemic, and it's still recovering now. But overall, the effect of the pandemic on temperature, at least ocean temperature monitoring, was minimal, which is really the good news, because the autonomous floats, the buoys and the Argo floats, continued to monitor through the pandemic, and even though the drifting buoys only last for 18 months, they did last through the pandemic. And you see on the left, that's the surface observing system, and on the right is the subsurface observing, and that goes back to 2000. And this kind of segues into looking at further back in time. You can see in the Argo era, when Argo was global, about 2006, 2007 onward, we had pretty steady, at different depths in the ocean, pretty steady measurements of temperature and salinity. Before that, you can see at 1,500 meters, in 2000, only 10% of the ocean was covered. And even at 300 meters, only 50% of the ocean was covered. So Argo is the backbone of the system, but as well, I'll just look at very quickly at what is done with these observations. And this is just marine heat waves from the daily about optically interpolated sea surface temperature, is observations of satellite and in situ together. And so this does show a good picture of marine heat waves over the last year. And when you look subsurface ocean heat content, and this is back to 1980, on the left, these are from the BAM's State of the Climate. And you can see there are different groups around the globe that are calculating ocean heat content from observations. And you can see in the Argo area, there's very good agreement. As you go back further, and these go back to 1993, you see less agreement because there are less observations. And you can see deeper down the bottom there, as you go back from 700 meters to 2000, there's even less agreement before the Argo. And on the right there, and this is from the previous IPCC report, you can see going back to 1950 with the observations that we do have, the uncertainty grows quite a bit. So what do we have going back historically? And this is looking at the World Ocean Database, which is an aggregation of ocean profile data from different sources. And you can see as you go back in time, and this is the number of oceanographic casts per year from the different observing systems. You can see the history of observing. Before 1950, there are very few. It's only bottle casts, and then you have mechanical bathythermographs, and then expendable bathythermographs, and into the modern era where you have the Argo floats, and also the moored buoys, the pinnipeds, the gliders. And so what this shows, the World Ocean Database is an aggregation of different observing systems, but the observing systems themselves aren't really observing systems. They're mostly research projects that are taking data for specific purposes, fisheries research or other physical oceanography research, decadal surveys, and pulling all that together to I guess cobble together an observing system over time. This is the mission of the World Ocean Database, and the variables in the World Ocean Database: temperature, salinity, of course, oxygen, nutrients, also tracers, some carbon variables, and chlorophyll, some biological. So anything from the subsurface ocean is gathered together. And looking at the changes over time, and you saw this in the atmosphere, the ERA5 talk, you have changes in the observing system. You have only bottle data in the 30s, then the mechanical bathythermographs. Now you could throw a sensor from a slowly moving ship, and that became the observing system, although there are still a lot of bottle casts. And then in the 60s, the expendable bathythermograph, now you could throw a sensor from a ship going at speed. So you could supply merchant ships and get all this information. So even pre-Argo, we do have quite a bit of information, although it's mostly in the upper ocean, and there are definite bias problems in the expendable bathythermographs. But the information is there, although lacking in, say, out of merchant ship lanes in the southern hemisphere. And then, of course, the Argo era, where we have much more complete coverage. And so this is all gathered together in the World Ocean Database, but it is not quite fit for purpose. That is all the data possible gathered together for essential ocean variables. There is an international group, the IQUAD, the International Quality Control Ocean Database, which then takes all of these data, uniform quality control, and adding uncertainties, and making these data, these observing data, more fit for purpose for reanalyses for ocean heat content. So some of the things done there is a lot of the metadata for expendable bathythermographs was not taken from the merchant when the merchant ships were dropping them, but it is important correcting and using for climate data purposes, reanalysis and other, to have that information. So gathering together old cruise reports and old information, and gathering together the information that is necessary to correct the data. Then assigning uncertainty for use in reanalysis and for other purposes. You need to know how good the measurements are. For instance, the mechanical bathythermographs, the depth and the temperature have a large uncertainty, the expendable bathythermographs as well. So gathering this information together is a mission of IQuad, putting it on the actual measurements and making that available so it's more useful to reanalyses and other purposes. And then gathering the expertise, global expertise to do quality control, a uniform quality control on the data. So the World Ocean Database is the basis for a lot of the data sets used in your reanalysis, the EN4 and the CORA. Those are reformatting of this database and different quality control. But it would be nice, because the World Ocean Database is continually being updated, continually changing and correcting information from historical data, it would be nice to have that one source for all of the reanalyses, or a continual update of EN4 and CORA and other data sets, so that they always reflect the community best standards. And so that is what IQuad is doing, gathering together the best quality standards and creating one data set that can be used across reanalyses and for other purposes. And so the World Ocean Database is also part of the UN Decade of the Ocean, is to try to get this data more available, more equitably available, openly discoverable, and access from the community to the World Ocean Database to upload data, and also access on the other side from reanalyses and for other purposes on the other end. So we have a standard set of data that is more international participatory. And so the idea is put the World Ocean Database in the cloud, and data and QC providers can add directly to the World Ocean Database there. And then users such as reanalysis can use it directly from that cloud source. Of course, there always has to be an internally consistent version that would be maintained at NOAA, but the external version would be a more globally usable for reanalysis and for the input community. And so what are the benefits of the World Ocean Database and Argo in the cloud? And I mentioned Argo here because the halosteric sea level change 2016 to present, calculated from near real-time Argo, is biased salty. So reanalyses, as you get further and further towards using near real-time data, you're going to be using the Argo salt salinity data in near real time. At the same time, those data are known to be biased, and those data are corrected over a period of time. A minimum of 6 months of data is needed to correct the bias in the Argo data. But if you continue to use, if you just download the Argo data and use it and never replace it, you're propagating that salty bias through your reanalysis. So if we have Argo in the cloud, and you can grab it and use it, either download it or use it directly in your reanalysis in the cloud, then you always have the most up-to-date data, and you have the bias corrected data. And likewise, the World Ocean Database historical data is always updated. And if the World Ocean Database is available in the cloud, then EN4, CORA, and other data sets can keep synced with the World Ocean Database and always have the most current data, and then the reanalysis will have the most current data. So the World Ocean Database is in the cloud, Argo is in the cloud now, but what is in progress is the development of a Parquet cloud-ready format for the ocean profile data, usable by both Argo and the World Ocean Data database. So if you have a uniform format, now if you have your reanalysis in the cloud, there's no more need to download. You can directly access this Parquet data, run your reanalysis, and this Parquet cloud format is always the most current from Argo and the World Ocean database. So your reanalysis is always accessing the most current Argo and World Ocean database data. So other data sets. So we do at the NCEI, we archive data from the entire ocean observing system, and the ocean profile data goes into the World Ocean database. But I also hear a need over the last few days for ocean currents information. And so we do have a global ocean currents database, and this gathers together drift data for from Argo, from the Global Drifter project, and it also from high frequency radar, from shipborne and moored buoy ADC acoustic Doppler current profilers. So all the ocean current data is gathered together there. So this could also be a source for reanalysis data. The International Comprehensive Ocean Atmosphere Data Set. I only heard one reanalysis using this. This is the in-situ marine meteorological and sea surface data. Oh, sorry. The Surface Underway Marine Database. Heard a lot about sea surface salinity as an input data set for reanalyses, but most ICOEDS does not include a lot of the thermal salinograph data, and that is a huge source of sea surface salinity data. It is a huge source of underway carbon data, oxygen data, and so on. And so this is gathered together through the GOSUD program and the Surface Underway Marine Database. We have an ocean carbon data system, the Marine Environmental Buoy Database. This is something I hear a lot of the regional reanalysis really need data, and a lot of that data is from coastal buoys. There's wave information, there's all types of information in the coastal buoys that's not gathered anywhere else, but this is a source where you can come for globally and get any data that is available there from coastal buoys and open ocean buoys. So there are a lot of other data sets that can be used for reanalysis that we gather together into databases at NCEI. And quickly, what do observationalists, what do we need from reanalyses? So this is a paper that came out recently on the ocean heat budget in the Gulf of Mexico by my colleague Zhangkun Wang. And there are enough data, temperature data, to understand changes over time in the ocean heat content of the Gulf of Mexico, which is a critical problem for understanding weather patterns and sea level change in the Gulf of Mexico. So that's something we can get from the observations, but what we can't is why the changes. And so the change in the ocean heat content is either going to be from surface fluxes, from surface heating, or from ocean currents coming in through the Yucatan Peninsula. And surface fluxes especially is something that there are very few measurements of. This is not something we can get observationally. This is something we can only get from other sources such as the reanalyses. And looking at the reanalyses, the surface fluxes are very different across the reanalyses. We ended up using echo for this because even the sign of the heat flux was different. Most models that we looked at, reanalyses, had the heat content, the heat flux going positive to the atmosphere, whereas echo showed, and ERA5 and echo showed heat flux, that the ocean is losing heat, ERA5 and echo, which matched what we saw from the observations, whereas other reanalyses saw gains of heat here. So we really need from the reanalysis an understanding of these variables that we can't measure so that we can understand the changes we see from observations. And as well, the ocean currents coming into the Yucatan, the heat exchange with the open ocean. those are the things to understand the changes that we are observing that is important to get from reanalyses. And so conclusion, and I know it's a trivial conclusion, but it is a truth. There's a great deal to be gained with a closer coordination between the observational and ocean reanalysis communities for an understanding of the ocean and the climate system. Thank you.
Thank you very much. As we have not so much time, but for 1 or 2 questions, please.
Yeah, no other question? Okay. So thank you very much for your presentation. So you mentioned a little bit in one slide, ICOAS. So that's a data set that we at C3S are working with a lot, because that we make it also available to Climate Data Store, because we also need it for our reanalysis, for instance, not only for reanalysis, but for all the users out there. So what is the relation between your World Ocean Database and ICOAS exactly? Are they all linked? And is it that the World Ocean Database contains more variables like biological values, but it also contains ICOAS? So how does that work?
It's yeah, I'm sorry I wasn't clear on that. It's actually the other way around. ICOAS contains the surface level of the ocean profile data from the World Ocean Database. That's the intersection. The surface data contained in ICOAS is not part of the World Ocean Database.
Okay. Any other question? I have a quick one, and if you could also connect to Slido, there are some questions, but we do not have time to tackle, so that we can discuss later, that you can answer them. It's a quick one on your last statement that we need benefit all if we have better connections between these communities. So where do you see the critical points where we should advance rather quickly in establishing these connections? What are the opportunities? For example, you mentioned that if with the access of data and most recent data, you would have also the best available data, avoiding if there are, for example, some problems in some data. But the problem is also maybe that there is a need to have a channel to communicate much faster, more in real time, that there are some issues in the data to the reanalysis system communities, because they also have another calendar in order when they restart the system. So, and also to understand also when they do the validation that there is maybe a problem that this is coming from the data, etc. So could it be ICOAD, or could it be through OPC, or what could be the opportunity to get this channel, for example?
Well, I mean, the observational community itself is always finding problems in the data, correcting problems in the data, and I think making those corrections and making those corrections available immediately online through the cloud to the reanalysis community is probably the best form of communication, but it doesn't, like for instance with the Argo salty problem, it doesn't alert the community. Okay, it may be fixed in the data set, but you're not alerting the community. So how best to have that back and forth of communication? I don't actually have a good answer for that. That is a really good question. I think interaction, such as in workshops like this, but there needs to be something more timely. And I don't know.
Discuss about it.
That's a good question that I actually wasn't prepared to answer.
No, it's for creating opportunities. That's why I asked this question. So let's discuss. Yes.
If I may add on this difficult point topic, I mean, if we're discussing on Argo, I mean, what is quite important is to really be aware on the different integrated products that exist. I mean, of course, World Ocean Database, Inform, and Cora, and so on, to make sure to document very clearly the level of the different Argo data that were used, in particular for delay mode quality control, because you mentioned, I mean, this is not always 6 months. For some profile, it can be all, this is real time and not delay mode. And if we distribute different data sets at different time, people forget totally. I mean, that some products, some Argo profile are real time, so not qualified, and they go into reanalysis without this clear information. And it's not easy because that's, but this is really close communication first between Argo community, Argo GDAC and so on the integrators. Or maybe, I mean, we should also come together on being able to process faster on this delay mode quality control, but there are issues on resources for this reprocessing. If you look at the satellite communities, there are work programs, I mean, ESA, NASA, and so on, to have really reprocessing activity for satellite with a lot of resources, and we don't have the same for in-situ. This is really a clear gap today.
Yeah, I agree. I mean, part of the problem, you're right that the Argo community doesn't have the resources to do as timely a delayed mode quality control as would be hoped. But even so, even if it was if they did have those resources, it still takes about 6 months worth of data to be able to do a bias correction. So you're never going to get that delayed mode correction, even fully resourced, earlier than 6 months after the initial measurement. Although Argo does make real-time adjustments as well.
Yeah, I think we have good opportunity to discuss. I'm sorry, I have to cut.
Yep.
I'm already a bad share because we are delayed. But different points to discuss. And so we have Raphaelle Sauzede now for the green ocean part on the observation. Thank you.
Hello everyone, it's working. Okay. I'm Raphaelle Sauzede and I'm working at the Laboratory of Oceanography in Villefranche, the LOV. And I will try to present you today biogeochemical observations to try to improve future green ocean reanalysis. Okay. So global biogeochemical ocean models are really important to investigate the current and potential future ocean state, its productivity, and also the cascading effects on higher trophic levels. But they are often tuned against data sets of inorganic tracers and also surface chlorophyll concentration from satellites, but more rarely on other biogeochemical parameters such as particulate organic carbon or zooplankton, and on the depth levels because of lacking in situ data. So I will try to present you today the data that I know the best. So I apologize because it won't be exhaustive and I may miss a lot of things that could have been interesting here. But I will present you some data sets because over the last few decades, there were a lot of efforts that have been dedicated to improve the accessibility and also the quality of oceanographic observations from the FAIR principles, and that help to have globally and homogeneously qualified data sets in open access. So in this presentation, I will present you first historical global qualified data sets. Then I will jump on autonomous platforms data, and then on observation-based products that are derived from these high-resolution data using machine learning techniques. Okay, so I'm not... Okay, so first about the historical global unified and qualified data sets, I wanted to start with a point that making interoperable different data sets, we can have a data set that can come in the past. So for example, here you have an example of a chlorophyll concentration data set that have been gathered from in-situ chlorophyll concentration, but also with ocean transparency data that have been converted using models in chlorophyll concentration. So it's become possible to have, for example, chlorophyll concentration data from the 90s. So you have here the temporal resolution of the data here used for this study, and also the geographical distribution of this ocean transparency converted chlorophyll concentration. And on the right here, I don't know. Oh, sorry. But it's not in the full screen. Sorry. And there is a pointer. I'm sorry. Okay. Okay. So just this three. Okay. Yeah. Okay. So here you can see the trends for this chlorophyll concentration data sets. So you can see that in the past we have larger uncertainties, but anyway we can derive some trends that I think are really important to this kind of studies. Now I wanted to point this very famous data set of GloFASv5.0, sorry, that gather high qualified in-situ data from more than 1,000 cruises covering the global ocean from 1972 to 2021. So this data set deliver data for salinity, oxygen, also nutrients and carbonate system parameters. We have dissolved inorganic carbons, so the DIC, the total alkalinity, and the pH. So this database provides high accuracy data that are highly qualified, and it's updated every year, sorry, for the carbon global budget. You can see here the geographical resolution of this data. So you can see that we have some areas that are poorly represented. This is one of the disadvantages. And also there is not so much data covering phyto and zooplankton. So concerning phyto and zooplankton, you have here the MareDat data set. So this is the geographical distribution of the MareDat high performance liquid chromatography marine pigments measurements that corresponds to the reference measurements for total phytoplankton biomass, so the chlorophyll concentration, and also the community composition estimation. So the MareDat initiative also provides other data sets for example, meso or macro zooplankton and some specific species for phytoplankton, for example, diatoms or coccolithophores. So the disadvantage of such database is first the geographical resolution with large areas that are not or poorly represented, but it's due only to the lack of in-situ data from oceanographic cruises, and also that there is no update since 2013. I wanted to mention here about this update that in our laboratories, the LOV, we have a pigment analysis service, SAPIG, where we have a regular update of the global database in terms of HPLC data, so chlorophyll concentration. And so we are preparing a paper in order to make available this data set and the regular update with a link to have this database in open access. So now I presented you in-situ data with some areas not really represented. So you will see now autonomous platforms data that have other advantages and other disadvantages. So from these new global data sets from autonomous platforms, we measure biooptical data that are high resolution proxies for biogeochemical parameters. So from these autonomous platforms, we have gliders, profiling floats, animals such as elephant seals, and also unmanned surface vessels, USV, such as sail drones or wave gliders, that only measure surface parameters. So you have here on the table all the parameters that are measured from each platform. What I wanted to highlight here is that some platforms measure the same parameters. So one thing that is really important is to make interoperable all the data that are measured from these different platforms. So this is a work that is ongoing. And we have these gliders that are more focused on coastal areas, elephant seas more on polar areas, and profiling floats that have a global array. And I will now focus on these floats, the biogeochemical Argo floats, BGC Argo. You have here the geographical distribution of the BGC Argo array right now, with these floats that measure, in addition to the temperature and salinity, 6 core variables that are 3 chemical variables, the oxygen, nitrate, and pH. You have also radiometric variables and biooptical proxies of biogeochemical variables like chlorophyll A concentration and particulate organic carbon. Something that is important to mention here is that these biooptical proxies can be linked to satellite data and correspond to the expanding of what is seen from this satellite. So from the current global array, we have more than 12,000 profiles of chlorophyll A concentration and POC per year. And we expect this array to grow to 1,000 profiles in the global ocean, so making these profiles more and more important, the number of profiles. Sorry, I missed. So to conclude on the plus and minus, so we have this high resolution data that I think that have the advantage to be interoperable by construction, and also we can reprocess homogeneously the database. So once we find, for example, a processing that we think improve, for example, the processing of chlorophyll A concentration, we can reprocess homogeneously the database. So I think it's really a good point, and it's comparable to the satellite reprocessing. But we have biooptical data that sometimes are hard to transform in biogeochemical counterparts. So it takes time to improve the quality of the database, but I think that it's better and better. So then I wanted to mention the new variables that are measured from these platforms. So for example, you have here the new sensor that is integrated to BGC Argo floats. That is the underwater vision profiler, so the UVP6. And thanks to this new sensor, we measure 15 particle size classes from about 100 micrometers to 2.5 millimeters. And we have also an onboard recognition algorithm that gives 19 classes of zooplankton. So here I present you just an example of the data that we can have from these new profiling floats. So it's here an example from a float that has been deployed in 2022 in the Labrador Sea. So we have this is here, the float, sorry, has been deployed during summer. So you have summer, then winter, and another summer period. So you can see here that small particles are sinking more slowly here. So you have small particles here and larger particles here that are sinking really faster. And you can see some different events of sinking particles. And again, for the second bloom here. So here it's an example for 2 size classes, but we have this for 15 different size classes. And here an example for zooplankton, so sorry, copepods here. You can see an increase of copepods here that corresponds to the summer bloom period. So they come to feed from phytoplankton. A second variable that is now measured from these new BGC Argo floats comes from these 2 different sensors that are integrated here. And both of them are sensors for hyperspectral radiometry. So one measures the downwelling irradiance, ED, and the other one, the upwelling irradiance, LU. So if you compare here the spectrum that we have from these different sensors, you can see here the natural fluorescence from phytoplankton. And what we expect from this new data is to have some information on phytoplankton community composition. And what I wanted to highlight here is that from these two sensors, we can estimate the reflectances that are directly measured from the satellite data. And so we can establish more direct link with satellite data. So here you have example of different reflectances spectrum for different areas. And we expect to have new information so on phytoplankton community composition from these floats, and also to facilitate calibration validation against satellite and to have maybe more interoperable data sets. So now I will present you the observation-based products that we can derive from these high-resolution data from profiling floats using machine learning techniques. So we can estimate from these BGC Argo floats new variables derived from machine learning techniques. For example, we developed a Canyon method that is called Canyon for carbonate system and nutrients concentrations from hydrological properties and oxygen using a neural network. So we derive from a Canyon B method at global scale and a regional approach for Mediterranean Sea, the Canyon Med method, nutrients concentrations, and also the carbonate system parameters, alkalinity, DIC, pH, PCO2, for every float that is equipped with an oxygen sensor and with data that are qualified in delayed mode. So we also deliver uncertainties with each estimate, and we deliver this data through a product that is released from the multi-op stack. And this product is updated every year and will be available in near real time from mid-2024. I think that all this data can be used such as any biogeochemical Argo data. For example, for data assimilation, there are the uncertainties associated. So I think that this is a useful source of information. I wanted here to mention that we also updated a method that allows to derive phytoplankton community composition from the normalized fluorescence profiles that is measured from BGC Argo. We have the phytoplankton community composition in terms of 3 size classes, but also for some pigments, diagnostic pigments, sorry, that can be associated to specific phytoplankton species. Here you have the distribution of a previous data set that we published from the previous method. This data set is available, make available chlorophyll concentration and the phytoplankton community composition for about 50,000 profiles from 1958 to 2015. So here I just wanted to show that this BGC Argo data and also the synthetic variables that are derived from the platforms can be used to improve biogeochemical models parameterization. So here it's a work from Quentin Hiverna that is in PhD between Mercator and the LOV. And he uses BGC Argo to tune the model parameters. So I just show you rapidly an example for the chlorophyll, nitrate, and silicate that is estimated from Canyon. You have in blue the BGC Argo seasonal cycle. In red and orange, it's the current models. And in blue and green, in black and green, you see the improvement of the models from his work and using BGC Argo data. And to finish, using machine learning, we also upscale BGC Argo data. So we developed a machine learning approach that uses as input satellite ocean color data with altimetry data, merged with the hydrological properties of the water column and the geolocation to retrieve the vertical distribution of chlorophyll concentration and POC. So we have this 3-dimension view of these 2 biogeochemical parameters that we deliver through the multi-op stack. And I wanted here to highlight that this method is now available for radiometric parameters and is in development for phytoplankton community composition. So to summary, we have these new platforms that have the data that are directly measured, but also all the data that we can derive from the machine learning. So I think it's a great source of information that could be really useful for models. And also, sorry, we have this so upscaling methods to have the three-dimensional view. So efforts have really to continue to gather and make interoperable historical observations, so in a unified and qualified global data sets to be consistent. I wanted to point that I think that we have to find a way to better connect biogeochemical in situ observations and the models in terms of how we do with units. For example, we measure something and we cannot sometimes connect with things that are in the models. Thanks to machine learning, there are new products and new variables that are available with higher resolution. And I think that we really have to construct together the future products to be sure that we provide the good requirements in terms of spatio-temporal resolution and also the accuracy in order to better integrate these products in future models and also to know what is missing for models. And thank you.
Thank you very much. So we are very late, but maybe one question. If someone has one question. So I'm just wondering in terms of the challenges you mentioned and the opportunities you have all listed. But I was also thinking, is there maybe an opportunity or is this already existing to have a dialogue? Let's say we had the opportunity of the physics community now and the biochemical communities and the physics community and made a long period, but you have also adapted new methodologies. The physical has not. So is there already a way of these interactions, or is that maybe another opportunity? And then together with a new linkage to the Reanalysis community to create this good opportunity. Now you think, is there already exchange ongoing with this physical databases or?
I think that there are exchanges. For example, there is this working group on biodata assimilation where we have exchanges and we present the products that exist. But I just wanted to mention that maybe it's before the development from our side that we have to make an agreement and maybe to push the communication before. I don't know how, but
important message. Thank you very much. And so I give on delay to the next session. Go with it.
So that's why I propose to do the coffee break now, but just 10 minutes. And I reconvene at, what time is it? 11 and 15. We reconvene at 11 and 15? 11:10, okay? In 10 minutes, and we have the last session in one slot, thanks to that. Thank you. possible improvement on some topics for reanalysis. And we will start with a presentation on data assimilation done by Luc. So, Luc.
Well, thank you very much, and thank you for inviting me to do this presentation. So I'll talk to you about the current existing multi-year or reanalysis system of the Black Sea, and then the future versions we envision for the next years. So this is work done together with my colleagues Anne Mouchet and Marie-Laure Grégoire at University of Liege and master and PhD students. Okay, so this is a famous VIRS image of the Black Sea, and the questions for this last session that we try to address in this presentation is which improvements can we bring to the models, the data assimilation part, and also using machine learning, and also questions related to observations. So which ones are available now to assimilate, and which ones exist in the pre-satellite era. So I will briefly present the existing system, and when I say the existing one, it's not the actually existing one now. It's the one entering in service next month, and then the rest of the talk will be dedicated to the improvements for the years after this year. And also the talk is targeted on my particular area, so the Black Sea, and there are some specificities. The Black Sea is a very stratified basin, and it's anoxic, so there's oxygen only in the upper layers. It's a riverine basin, so the salinity on the surface is quite low, but it's higher at the bottom. And this leads to the formation of a lot of clines, so the halocline, nutriclines, oxyclines. So there are sharp vertical gradients, and these gradients are quite difficult to maintain from a numerical point of view during very long simulations. So if you have even a little bit too much of vertical diffusion, for example, in the case of the salinity, salt will be diffused upwards and will compromise the quality of the simulation. Another thing is that some biogeochemical variables are strongly constrained by the physics. So for example, oxygen oxygen concentration is dependent on temperature, and others are less dependent on the physics and more dependent on the other biogeochemical variables such as plankton. And so in order to have the big picture right during a very long simulation, both of the components, physics and biogeochemistry, need to be right. So in order to try and solve these problems in 2023, so this year for the new product entering in service next month, we switched to NEMO 4.2. We changed the vertical grid to have a higher concentrations of levels around the depths where the vertical gradients are the largest. We changed the diffusions to schemes horizontal and not horizontal, lateral and vertical to try to reduce the spurious diffusion across the clines. And we also worked, of course, on the biogeochemical model itself. About data assimilation, for now, in this version, we will use a seek filter. So we are not using NEMOVAR or the variational methods, but sequential ones. And the error of the model error covariance matrix is approximated by some EOFs obtained from a long precedent run. And we have something maybe specific is that I think most reanalysis, when they perform data assimilation, use a horizontal localization method, not trying to limit the impact of spurious correlations at long horizontal distances. We do this as well, but we also try to do it in the vertical. So we consider, for example, when assimilating surface observations like satellite chlorophyll, that the impact of this information shouldn't be propagated to depths. And then the new thing we implemented this year is that the depth at which the impact of the information is limited is depending on the mixed layer depth. So it's computed pointwise by the physical model and taken into account when propagating information obtained by the data assimilation method. And with all of these features, we assimilate level 3 multi-satellite chlorophyll images obtained from the CMEMS catalog. And this is an example of a data assimilation increment on one of the first days when the satellite images become available in 1997. And as we assimilate L3 images, there are clouds and some parts of the basin are not corrected. So this answers partly the question of what satellite images do we use now, or what observations are available for data assimilation. And I will come back to this question later in the talk. We also have a problem typical for our model, maybe, is that up to the previous version, at least, chlorophyll was not a prognostic variable in the model. It was deduced from carbon and nitrogen content in the phytoplankton groups. So from carbon and nitrogen, we deduce chlorophyll, and then we sum the chlorophyll over the different phytoplankton groups, and then we have chlorophyll that we can compare to the satellite images. And after data assimilation, the question arises how we propagate this correction back to the carbon and nitrogen components. So the traditional solution would be to have a multivariate covariance matrix, and automatically corrections would be propagated to the other groups. And of course, this supposes that there is a linear relationship between the different variables. In our case, we used a different approach. So we compute a ratio between the analysis and the forecast, and then we multiply each of the components with this same ratio. So the ratio is obtained as the analyzed chlorophyll divided by the forecasted chlorophyll, and then we can use this multiplication to all the components, so carbon, nitrogen, and chlorophyll for each of the phytoplankton groups. And so the ratios between the groups and the ratios between the different constituents in each group are unchanged by the data assimilation procedure. So this may be a better way or not. It depends on particular cases. And with all these methods and all these choices we made, we produced for this entry in service a new simulation. In the catalog, it's available from 1992, but we actually started in 1980. And starting in 1997, data assimilation of chlorophyll, satellite chlorophyll images comes into play. And the results of this new simulation look quite better than the previous version. So oxygen is improved, mainly thanks to improvements in the physics and in the grid and in the diffusion methods. Nitrates are improved at depth because we better constrain the nitrocline. They are somewhat degraded at the surface. Phosphate is strongly improved during the period, at least we can say that during the period when we have phosphate observations. So essentially from the beginning of the simulation to the late 90s. Chlorophyll is improved both thanks to improvement in the model and to data assimilation, and the other variables are mostly unchanged. And this brings us to the second part of the talk, where I want to ask some questions or propose some ideas of what we would like to do for the future versions. And the outline of the changes would be that for next year, we will try to propose an extension and start the model from 1950 instead of 1980 or 1992. In general, what we would like a lot is to switch to a future version of NEMO. I don't know which version, and I don't know when it will be available, but it's in the plans to switch from a leapfrog numerical scheme to a Hunchkuta scheme of the third order, maybe, which would alleviate the need to filter. And this filtering with the Aslin filter is causing a lot of trouble for us because it produces overshoot and undershoots, and then we have to do clipping, not to have negative concentrations, etc. So it's really a pain for the biogeochemical model, and we hope that this switch will solve a lot of these problems. Then we would also like to switch to an ensemble method instead of a deterministic forecast, and use an ensemble Kalman filter instead of the Sieg filter. We would like to include an optical model. We would like to change the method to compute chlorophyll. So instead of being a diagnostic, it would be a model prognostic variable, and this change has actually already been done for the version of this year. We would like to improve representation of suspended particular matter, and we would like to go to parameter estimation instead of state vector correction. So the first point was to extend backwards in time to 1950, and here we have two problems. One problem is to obtain an initial condition, which is which is not possible only with observations. So in 1980, the model is initialized from a climatology built from observations around that period. In 1950, there are not enough observations, so we have to do it by means of the model. And the method is to run. The method is to run the model by repeating 40-year simulations a lot of times until we obtain some equilibrium state, and then we start from that. And during these repeated cycles, we use atmospheric forcings for the period in question. We also use PCO2 from the pre-industrial period. We also use river forcings with less nitrates, less phosphates, and more silicates corresponding to estimates of the river loads in the pre-industrial period. The problem is that during these very long simulations, many centuries, the model is not able yet to maintain the sharp vertical gradients that I mentioned before. And so we are still working on that. Other features of the model are realistic, like the cold intermediate layer in the model is very realistic. So we're quite happy already with that. And then the other problem when extending the simulation back in time is the observations available. And in the case of the Black Sea, it's maybe an uncommon case, but actually there were more in situ observations in the 60s and 70s, etc., than in the recent period. So during this period, there were many in situ cruises like the NATO for Peace program. And so we have actually many biogeochemical observations in this period. So this is quite good news for the Black Sea. In the recent periods, there are actually, so the last years, there are actually very, very few cruises in situ. And so the only thing that not the only thing, but essentially the only thing that we have now is biogeochemical Argo measurements, and they are limited in the deep sea, and also they don't measure all of the parameters that were measured before during the cruises. We would like to switch, as I said, to an ensemble method, and then we have developed some perturbation methods to generate perturbations in the biogeochemical. We also perturb the forcings like the atmospheric fields and the river inputs, both for water and for nutrients, and the biogeochemical parameters themselves. We run ensembles with each of these perturbations individually. So we run about 30 ensembles to study the effect of the perturbation of each of these things. And then when we will be happy with them, we will run a final ensemble with all the perturbations applied together, which will hopefully give us a sense of the real uncertainty affecting the forecasts or the reanalysis. So this is an example of the spread in the ensemble when we perturb the freshwater flux in the rivers. In this area, there's the Danube River flowing to the Black Sea. So of course, we have a very large impact on surface salinity where the river water is perturbed. But sometimes more surprising results appear, like, for example, if we look at the surface velocity, we see a large spread at the shelf break. So this part is very shallow, and the rest of the basin here is very deep. And the velocities at the cross-shelf exchange area are quite impacted by the perturbation of the freshwater flux. Another thing that we would like to do in the future is to include an optical model. So the target is twofold here. We want to improve the biogeochemical model itself, and also we would like to switch from assimilating chlorophyll images to assimilating surface reflectances, because it would allow us to assimilate something that is closer to what is physically measured by the sensor on the satellites. So this is something that is similar to what is done in the MED already this year for the near real-time product. It's based on MIT GCM and Darwin biogeochemical model and the RadTrans optical model. It simulates the propagation of light at different wavelengths, and for the direct light, so the downwelling light, the diffused and the backscattered components of the light. The boundary condition at the surface is coming from an in-house atmospheric model called MAR, and into MAR we added ECRAD, which is the ECMWF radiative transfer model. And the absorption, diffusion, and backscattering depend on all the optically active constituents in the water column, so water itself, chlorophyll, sedum, and particles. And so the idea now is that we have to have, in the model, we have to put we have to concentrate on the correct representation of these three categories, because it will be the ones that influence the light. And actually, this work will, in theory, this work will go into service in the Siemens catalog next year, but just for the near time product, not yet for the reanalysis. So as I said, the impact on light is the sum of the impact of different constituents in the water column. So we have to extract this information from the model variables. Then we solve a system of equations and obtain the direct diffused and backscattered components of the light at each point in the water column. And then we can compute the reflectance of the surface as the ratio between the reflected light and the incident light. And once we have this method working, we can also include it in the ensemble that I just mentioned before. And one parameter that seems critical to perturb, or one parameter that is affected by a lot of uncertainty, is the CDUM concentration. So CDUM in the Black Sea at least has a very large impact on the absorption of light, but it's not a model variable in our case. So to represent the absorption by CDUM, we have to use estimates from biogeochemical Argos. And so we made a kind of climatology and did use a yearly cycle of absorption by CDUM. So this is already the absorption multiplied by the concentration of CDUM, since we don't have it in the model. And by using that, we obtain some estimates of the light, like the free model is in blue. And we can compare it to the biogeochemical measurements of light, which is the red curve. And if we perturb the absorption of light by CDUM, then we can get closer to the measurements. And for example, if we have a perturbation intensity of 50%, then we can obtain the yellow curve. And this improvement in the representation of concentration and absorption by CDUM is also consistent in time. So this is just a vertical plot of the visible light in this case, and light at 490 nanometers in this case, but it's also consistent during the year. So there's less light in winter, more in summer, less when there's a bloom and more absorption. But in all the cases, the perturbation and the stochastic method seems to improve the simulation. And then once we will have this optical model and its perturbation in place, then we would like to assimilate surface reflectances rather than surface chlorophyll. So the OCTAC computes surface chlorophyll in the Black Sea by separating the open sea and the coastal region. In the open sea, they first compute the ratio between reflectances at two different wavelengths. It gives us take the logarithm, and it gives us variable r, and then there's this function combining this variable r, and finally it gives us the logarithm of the chlorophyll. So it's quite a heavy processing to obtain a variable which is not so close anymore to what's really sensed by the sensors. And in the coastal area, it's even more complicated because it's done by a neural network. So this is not necessarily meaning that it's a bad estimate. It's actually already very consistent with the model, but still we would like to rather assimilate something which is closely related to model state variables. And so we will try to assimilate directly the reflectances instead of the chlorophyll. It should be noted that in this case, the inversion problem is even more complicated than before. So now we have these reflectances and we correct them, but how do we go back and propagate this correction back to phytoplankton or even to nutrients? Okay. So we might alleviate this inversion problem by not updating the state vector anymore, but updating their model parameters. Another variable that should be improved in the model is the suspended particular matter. And in this case, the improvement is also, or the quality of the SPM representation in the model is also very dependent on waves. So we will try to work on the combined effect of currents and wave on the suspended particulate matter. It is also dependent on the chlorophyll content in the water column. So now, as I think I mentioned before, we will have chlorophyll as a state variable rather than a diagnostic variable. And it's actually improving the chlorophyll representation already now. And we hope to better tune the parameters and improve it more in the future versions. And even if we had all these corrections, even if we had an ensemble, even if we had the optical model, we still couldn't do what we want to do, which is to propagate an ensemble during a period of 40 years, maybe, or more, 70 years, because we don't have computing resources for that. So the configuration that we use now takes about 30 hours to simulate 1 year. So if we want to simulate 70 years, it takes quite a lot of time. If we add the optical model, it will roughly double the computing time. And then if we want to run an ensemble, it becomes impossible. So what we would like to do is try a new method, which is called super resolution. The idea is to simulate the ensemble at a lower resolution. So in our case, 6 times lower. And then do 2 simulations, one with a full resolution, one with a low resolution, by applying downscaling from time to time. And this gives us 2 data sets, and then we will try to use artificial intelligence for generating an upscaling method. So from the low resolution ensemble, try to obtain high resolution. This method we try in collaboration with NERST in Norway. They already applied it in their domain with some success on physical variables. And we would like to try it on biogeochemical variables. And this would help solve the problem of computing time. So this is kind of a summary of what I said until now. If we manage to do all these changes, then hopefully biogeochemical variables will be better represented and their uncertainty will be estimated. Also, light will then be better represented and its uncertainty will also be estimated. An ensemble can be simulated in reasonable time, and then hopefully we'll be able to estimate the nominal resolution ensemble forecast. And then with that one, we can use an ensemble Kalman filter at high resolution and assimilate physically or closer to physically observed variables like reflectance. And then we can think of using this assimilation to update model parameters rather than the state vector. And with all of this, the errors of the day will be reduced. So that's also very optimistic. So we say errors of the day, supposing it's just errors of the day and no systematic biases, for example. And then we go back to step 1. To successfully perform this work, we also need more data. So we have rough estimates only of the river fluxes in the 50s, 60s, 70s, etc., and almost nothing for the nutrient loads during this period. And we also have a very big unknown in the model, which is the atmospheric deposit of nutrients. And I would like just to mention that we also continue to work on the biogeochemical model itself. Thank you.
Okay, thank you, Luc. Maybe as we're a little bit out of time, we can, if you have a question, I propose to use a Slido, if you agree, and you can answer on it, but thanks again. And as you are talking about IA, etc. method, machine learning, we have now Ronan, who is presenting the next talk. Intituled Leveraging Deep Learning for Ocean Analysis OYR11.
Okay, do you hear me online? Yeah, I won't do this. I'll do okay, what's wrong here? Sorry. Okay. That was ready. Okay, good. Okay, here we go.
Yeah, not in the right mode. Yeah.
Okay. You can let me know when I have 2 minutes left. Or okay, fine. I can that way. Okay, great. Okay, good morning, everyone here. I'm Ronan Fablet from EMP Atlantic, and member of a new research group, which is some INRIA team, Odyssey, which is a new introduced video group in between AI. Yeah, it won't work. Okay, then we'll do it that way. No worries. And people from ocean science between IFRMER, INRIA, and IMT among partners. So today, following some discussion with Julien, especially and many other people, I'd like to discuss how we think deep learning, especially can benefit and contribute to ocean reanalysis, and initially with 3 points why we think that this is timely and how we could proceed to implement those ideas, and probably when we expect this to be useful or move to be some operational level. Okay. So probably first point, which is why that might be relevant to explore those approaches. There have been many talks during those 3 days showing that quite relatively the skills of the ocean reanalysis, but still there are some limitations. I may point here two aspects to which I would expect deep learning to contribute to. The first one is probably, as illustrated by Raphaelle in previous talk, the ability to better exploit observation data set, like the BGC-Argo, for example, but also think to high-resolution satellite data, where I would expect learning ideas to make best use of those available data set. Another one is the representation of the variability of a system. So currently, it's mainly based, in my understanding, on ensembles with just a few members. So with just a few members is very difficult, obviously, to represent the full distribution of the ocean states. And again, here, especially regarding the reduction of the computational complexity using deep learning, that could probably be means to enlarge a lot the size of the ensembles, moving from a few to probably hundreds, or we'll see, or provide other ways to represent the variability. So that's first point for the why. The second one is from a machine learning point of view. If we, on my side at least, when I try to understand what's the way ocean data assimilation or data assimilation systems are built, I look at this as basically a Lego game with 3 main components, like an ocean model, like NEMO, some observation model to link the observation to the state, and then some assimilation, your preferred assimilation scheme. Could be ENKF, could be a 3DVOR, 4DVOR, and so on. And so meaning that the data assimilation system is a composition of elementary blocks, okay? And the thing is, there have been a number of demonstrations over the last 10 years that using learning, you can learn any kind of thing. You can learn PDs, ODs, you can learn solvers, you can learn optimizers, you can learn operators, and of any form, from whatever kind of data as input to whatever kind of data in terms of the structure of the data. So meaning that for sure there are ways to use those ideas to revisit the way we can build ocean data assimilation system. That's the first row here. And the second one, which is also important, is that in the way we calibrate a learning system, there have been also many new ways to calibrate systems. So, and basically not only based on the typical mean square error minimization. So there are many other ways, especially more looking at the data in terms of the way we can get the same type of distribution and some data sets. So more in some kind of looking more at the variability than the actual state. So that's also probably something very interesting that could be explored at some point. Okay, so coming back, so then moving to the how, knowing that we have like elements to think that's relevant. So going back to the way we can look at the ocean data assimilation system, probably the first option is and that one mentioned regarding the super resolution data assimilation developed by NERSC.
the idea is to use deep learning to represent or complement one of the system or one of the components. So basically in the super resolution data simulation that was mentioned in the previous talk, the idea is to use some learning ideas to represent the observation model. You could think doing exactly the same for the ocean model at some point, or the assimilation algorithm, okay? Here, you see that the goal is to use some existing framework and to replace one component, okay? And that's for sure probably the option which is the simplest one, probably to move to some operational system in a short term based on learning ideas. From a learning point of view, it seems more natural. Sorry for this. Okay. When you look at the goal of the ocean reanalysis, you can look at this from a machine point of view. The way you look at it is that you provide to your system as input some observation data, and what you like to retrieve as output is some full state over some time extent. And because I told you that basically what's a learning algorithm is a way to map some inputs to some outputs. So it would be really natural to try to not only replace one component, but to try to replace the entire data simulation pipeline or ocean reanalysis pipeline by a learning scheme. We use the term end-to-end learning to refer to this kind of ideas where the goal would be to learn the entire inversion scheme. Here again, there are a number of examples for this. I've listed 3 here. The first option is really just to use classic NOR architectures and apply them to try to address a specific inversion problem. And there are also options where, and we've been contributed to this, is more to try to build NOR architectures or deep learning schemes which rely on some data assimilation formulation. So on our side, we've been investigating 4D formulation, and people from Toulouse here and some of the groups have been investigating neural networks based on some extension or generalization of sequential data simulation framework. So I won't review this. I would just explain briefly what we've been doing on our side, but I'll provide some references for the work from people from Toulouse. So just to mention, the goal here is not to explain in details how it works, but just to mention that there are ways to build neural networks which are explicitly based on some variational formulation of the data assimilation problem, meaning that the reconstruction of the state is stated as the minimization of some variational cost, which is what you see here with some observation term and some representation of the dynamics of the prior. We can make some explicit relationship to some weakly constrained 4D formulation. And what's different here is that the different operators can be learned or can be set a priori. And what we can also learn, and that's probably the most interesting part, we can learn the way to optimize the variational cost. And we try to get the best possible solvers to get the best possible reconstruction of the state given the variational formulation. So now you have on the right for you the what we call the computational graph, which is some representation of a neural network. So I won't go through this, just here maybe to mention this. Here you see gradient, which is the neural version of the computation of the agent operator. So what's really interesting here in neural networks is that you get the automatic differentiation. So we don't have to recode the agent for the dynamical operator and for the computation of the derivative for the rational cost. We got all this for free because we use a differentiable programming framework. So that was just some word. And here an illustration of a direct application of this framework to sea surface height mapping for real altimetry data. And here you have a comparison. So on the left for you, the first column is the 40 Vandet scheme applied to satellite altimetry data. The second one is the GloRIS reanalysis. And the third one is the DUAX optimal interpolation product. And you see numbers here, so which refer to the results scaled by the different interpolation scheme. And you see that we get quite some improvement using the deep learning scheme, going down to about 100 kilometers compared to the 150 by Aviso. This is just for a 10 degree by 10 degree box for a Gulf Stream area. But and probably what's more interesting to me is that it's not really obvious here on the screen, but I could show you the animation here. It's slightly higher resolution, I would say. Basically, when you look at the gradients of the deep learning interpolation are more similar to the gradients of the GloRIS product. At the same time, if you look at where are the different structures, they're more similar between the deep learning and the Aviso product, because all those two products are based on the observation, okay? And so probably they better fit, and clearly they better fit the observation, while the deep learnings provide something more realistic in terms of the geophysical structures. Okay, so here, so we are more, this is more some kind of proof of concept. So showing that it seems to be a relevant path to push forward. And there are many also examples. And currently, in my understanding, my knowledge, most of those demonstrations are for a single parameter. Previously, that was the sea surface height, and mainly for sea surface parameters. Okay. And for let's say a region, a small region of the ocean. Before that was a 10 degree by 10 degree box. So probably the question is whether we can move to a global scale. I don't think here there's really some, so we're ready probably in terms of computational complexity to move to global scale. So the question probably more is, can we move to 3D ocean states? And that's probably, so I'm not able to answer this yet, and that's probably the next challenge, really, to move forward into this. So I've just illustrated here in the same way as illustrated by Raphaelle, also some works where, but more, not exactly the same kind of learning ideas, more some kind of really observation-driven techniques, proving that you can also apply deep learning ideas to get some reconstruction of 3D fields for the ocean, here for temperature and salinity. Raphaelle, that was more for BGC. But the difference here is that those techniques do not try to bridge models and observation. They are only currently based on observation data. So the next step could be to explore those neural data assimilation scheme to get this ability to bridge modeling capacity, model skills and observation and data. Okay, some summary here. Yeah, I've illustrated that you can investigate different ways to use neural schemes to complement or replace for task-specific purposes data assimilation schemes. I really look at this as a different way to bridge models and observation data. Instead of using ENKF or 4D-VAR, using learning to map somehow models and okay. Yeah, I move to the so one important thing is this end-to-end learning idea, and the fact it's really task-specific, task-oriented, or user-centric or application-centric, whatever term you would prefer. But when you learn a system, you need to define the metrics on which you're gonna train your system. So that will be your performance metrics. So meaning that you optimize your system for a specific task. So that could be great, and then you may question the generalization properties, okay, for sure. But that's very different from, in my understanding, from the design of some ocean data simulation system, which is very generic and then can answer all needs, but is not optimized for a specific need. So probably trying to bridge the two is very meaningful. The last point I think is also particularly important in that the one obvious gain in using deep learning that intrinsically we use differentiable programming techniques, which are that we can run on any kind of GPU, CPU. It's very high level, so we don't care about the hardware. So it makes your life much easier in terms of implementation. And maybe to mention here, all I've presented can run on a laptop. Okay, so you don't need like a supercomputer to run learning. Okay, it's way simpler. How much time left? You don't. 1 minute. Okay. And some slides regarding next steps. So I won't go. Here it was some illustration related to the model correction discussion, showing that you can use the same kind of end-to-end learning ideas to address model corrections. Here, that's an example for null closures. So just to mention that we've been working on this with Julien especially, and some reference. And probably, yeah, I use this one. And the last one. In the experience regarding the SSH sea surface height mapping experiment, we gained much experience and we've made very good progress, I think, because we use some collaborative framework and especially the design of data challenge. So that relates to the intercomparison discussion that was raised yesterday, I think, or the day before. I do not remember exactly what wrote it. That goes way beyond a beauty contest, okay? And I really think that we made good progress in the way we can design the experiment, the way we can design our networks, the way we can compare, the kind of thing we can really address, because we had this collaborative framework, and including baselines corresponding to operational systems. So that's probably way more important to have those kind of things within the if we want to move forward into deep learning. And on our side, we've been developing with the team in Grenoble and Julien, this ocean bench. And for those interested, I invite you to look into this. So that would be it for me, just some acknowledgement and reference for those who would like to read more about our work. Thanks for all.
Wait, thanks, Ronan. We have time for 1 or 2 quick questions. Yes, Hans.
So is it correct that your machine learning algorithms or your deep learning is mainly acting on the data simulation system of the ocean reanalysis?
You mean the 40VAR or the system we use?
Yeah. Whether your focus is on doing the data simulation system with deep learning, is that's what you try, is mainly the data simulation system, or is it the model itself?
No, on our side, we explore more the end-to-end, where we try to replace the entire data simulation by a deep learning scheme. And what's specific in our approach is that the deep learning scheme is based also on a variational data simulation formulation.
Okay.
So we'll still have some observation model and some representation of the dynamics, for example. And then we could use some PD representation of the dynamics with the solver explicitly.
Yeah, because the reason I ask is because people are doing now machine learning for weather forecasting, and they're quite successful. And one of the reasons they can do that is because the verifying analysis, they have it very accurately, you know? So because it's just a forecast and you look at the verifying analysis, when you do machine learning for data simulation, so you have a very good high quality training set. For data simulation, what do you use as the training set? Do you use the current data simulation you have, but you want to improve on that, you know? So then you create something which is as good as what you had, but you want to improve on it. So to have a good training set for data assimilation is more non-trivial than the application of machine learning of forecast. Do you agree? I mean, do you agree with that statement?
Not sure. Okay, I'll try to explain. The example I've shown, the model for the SSH mapping, the training of the model is based on simulation data. We've used an OSSE setting with a NEMO high-resolution simulation, and when we've simulated the satellite observation, we've trained on this, and this model trained on simulation data was applied to real data. Okay, so and we checked that we get very good performance, and then we were thinking that depending on the simulation data set we're going to use, we may impact a lot the performance. So we had some training with the same kind of strategies using DUAX, so the Aviso product, which is not very good in terms of a gradient, using GloFASv4.0 reanalysis, or even a very coarse 1/4 of a degree model, which is not, if you look at this for Gulfstream, I mean, the Gulfstream is not the Gulfstream, right? Still, when you learn from this, so you lower a bit the performance, okay? It's not that the interpolation is much better than the kind of representation of a Gulfstream you see in the simulation. So what I mean here is that it's not fully clear yet what would be the best, or there are probably many different options on many different data sets from which you can train a model and get good performance, and not only the best and most realistic ones. So that probably is something we need to understand more, for sure. But it means that maybe idealized simulation might be very relevant for learning some inversion algorithm. So yeah, so it's not exactly the same setup as the ERA5, where I mean, the goal is really to do some forecasting, and the reanalysis, I think, is somewhat different from the forecasting problem in terms of the way it can address this from learning ideas. So maybe I think that the conclusion drawn from the reanalysis and forecasting, ERA5 and weather forecasting, may not apply to what I've shown here for more some kind of space-time interpolation problem.
Okay, thanks a lot, Ronan. I propose to move on the next talk, which is an online talk given by Mike and Matt, our colleague from UK Met. Mike, you can put your camera on if you... Yeah.
I don't think I can share my video. Perhaps you can run the slides. Can you hear me okay?
Okay. We will
perhaps you could run
have your slide, yeah.
Mike, I could try and share them if you like.
Yeah. So whilst Matt is trying to share his screen now, that's good.
Yeah, okay. So
hi. This is a talk by two people, myself, Mike Bell, and Matt Martin. I've been the chair of the NEMO Developers Committee for the last 5 years or so, and Matt is the leader of the Marine Data Assimilation team at the Metoffice. I'm going to be talking about potential model improvements for reanalyses, so that's ocean model improvements. And Matt is going to be talking about a correction of biases by methods for correction of biases by data assimilation. So if we move on to the next slide, this is quite a large area, and I'm only going to discuss physical ocean models. And these slides cover more things than I can go through in 10 minutes. So I've just got 5 slides which discuss firstly representation of mixed layer processes, where I think there's plenty of potential for improvement. Then making best possible use of horizontal resolution, and some of the is about taking care to do things rather than with the existing tools that are available, rather than improving the tools. And some of it is about about making best use of the tools that are available. I'll then talk about some of the areas of the models where there's low order accuracy representations and where there's definitely room for improvement. And then as a second one, which is about taking care to make sure that there aren't unphysical transfers or cascades of energy to small scales. So on to the next slide, please, Matt. And this just represents the variety of processes, physical processes that take place within the mixed layer. So currently, most mixed layer models represent convective processes and also shear-induced turbulence. It's not so common for the mixed layer models to represent Langmuir turbulence, but that does have much stronger downwelling motions and which can affect the entrainment at the base of the mixed layer, which is really what we want to represent in our models. You can have near resonantly forced inertial waves, and there's a whole zoo of sub-mesoscale processes which are reviewed in this quite nice recent review by John Taylor and Andrew Thompson. And there's also turbulence below the mixed layer that you need to represent properly near the equator. So consistently capturing these things in these processes is something that we can do much better. On to the next slide, please. This just talks about the impact of horizontal resolution. So I think most people will be fully aware of this, but on the left, it shows the impact on the surface current speeds of just increasing the horizontal resolution of an ocean-only integration. And you can see that at 1 degree, that the Gulf Stream is really very sluggish. And the colors here represent the speeds, and even the direction of the flow isn't right in the region of the Grand Banks and the Flemish Cap. And so going to 1/4 and 1/12 of a degree is really essential to represent the main processes that are going on in the model, the advection of the temperatures and salinities by the flow. Going to higher resolutions, which is shown on the right, does have some impact, but it's much less than the impact in getting to the mesoscale represented. I should say that reanalyses should be less dependent on the resolution than just ocean-only integrations. But even so, I think the reanalyses, getting to 1/12 of a degree resolution for this sort of region is really quite important. So on to the next slide, please. There's a lot of text here, and I don't intend to go through it. But to make horizontal resolution is very expensive. So if you decrease the grid size by a factor of n, then the computational cost goes up by about a factor of n cubed. So 1/10 of a degree model is about 1,000 times as computationally expensive as a 1 degree model. So you really want to make sure that you're making best use of your horizontal resolution. And it's really quite important that when you're advecting traces and momentum around, that you use at least a 3rd order upwind scheme. There's some explanation here of what the effective resolution of a model, how you can assess that. And the main point here is that 1/4 of a degree model doesn't really resolve the mesoscale even in the subtropical waters. This just shows on the right the near surface kinetic energy spectra this is near surface in some very high resolution models, so it's grid spacing from 2 kilometers to 20 kilometers. And you can see that the 2 kilometers has a different kinetic energy spectrum as a function of the wave number. I think, and I should just mention that the dashed lines show the NEMO simulation, and the red show the ROMS simulations. So ROMS was using a better dynamical core at the time, and NEMO version 5, which should come out next year, and use runner-cutter integration schemes. That should give similar sorts of performance to ROMS. Go on to the next slide, please. Yeah, so attention to very low order representations. So in our models, the coastline is represented by a series of steps. So if the grid is aligned with the boundaries as it is on the left-hand side of this figure, the flow, it's quite easy to get the flow to be slippery along the boundary. But if the grid is rotated at a 45-degree angle, then you can see that in the little circles, you can see that the boundary itself it is quite sort of sawtoothed, and it's harder to get the flow along the boundary to be free slip. So with one formulation, the one in the middle, the free slip solution, you don't get the proper free slip solution, whereas using different set of boundary conditions on the right, you can get a good free slip solution. There's a similar sorts of issues when you have vertical steps. So with Z coordinates, you've just got a series of vertical steps that the flow has to go down. And this is well known to cause various issues. And so there's a lot of good potential for terrain following coordinates or more nearly terrain following coordinates. It's been which the NEMO model will move in that direction, and also start to implement generalized vertical coordinates, which have been described in these papers. I think I'll move on to the next slide in the interests of time. This is the last slide. So one needs to be a bit careful with model solutions to avoid grid scale noise in the velocities producing diabatic mixing from numerical errors in advection. And the paper by Ilikak is a good reference for the sorts of things that you need to do. And using a third order upwind momentum advection gives some advantages in that region. This figure just shows that it can be quite important to get the numerics of the ocean model correct. So it just shows that there was the scheme that NEMO was using, an energy and entropy conserving scheme, which was derived by Arakawa, that when the horizontal resolution gets to be high, the original scheme had a very poor representation of the eddy kinetic energy. So this is a high resolution model, and when the model was corrected to avoid a direct transfer of energy from the zonal flow directly to the grid scale, with this high resolution model, you got a much better representation of the eddy kinetic energy, which is on the right hand side. I think that I'll leave it there so that Matt has some time to go through the bias issues. You're muted, Matt.
Hi, can you hear me okay now?
Yes.
Can you hear me?
I can, Matt.
Yes, go, Matt.
Can you hear me? I'll keep on.
Yes, we can.
Mike, can you hear me?
I can hear you, Matt. Yes.
Matt, Mike?
I can't hear somebody from the room. Well, I'll just
we can
carry
hear
on.
you.
So I was going to talk about model bias and data assimilation. So the biases come from various different sources, as we've heard various times this week. So the model itself and the surface forcing and the observations can all be biased. You can also get bias in reanalysis due to the error covariances in the assimilation causing them. And there are also interactions between the increments in the model which can generate biases. So you can use average increments to diagnose biases from assimilative systems, as well as using the innovations as well. But so ideally what we want to do is to try and understand the cause and reduce the sources of biases, but they can also be corrected as part of the data assimilation. So I thought I'd just give a bit of a overview of how to correct the biases in the DA, but then also look at some specific causes of biases in our system. So on this slide, I'm showing an example of some mean increments from the foam system reanalysis. So this was an reanalysis that was carried out at 1/4 degree resolution, and it uses a 3D VAR assimilation every 5 days. Assimilates satellite SST data, so level 2 satellite data and in-situ data of SST, together with profiles of temperature, salinity, and sea ice concentration. And for the SST data, we include a variational bias correction scheme. In the increments here, we're not including the SLA assimilation because that can complicate the picture of it in terms of the model biases. But the plots are showing the average increments over the particular season over the period 2004 to 2016, where you've got all the Argo data. In this case, it's March, April, May, and it's showing them at 3 different depths. So top of the surface, then about 50 meters, and then just about 100 meters depths. And so you can see that for temperature, there are large negative biases in the tropics at the surface, and there are some smaller positive biases at mid-latitudes in the temperatures. And because it's a 1/4 degree system, you get biases in the Gulf Stream and the Southwest Atlantic and other sort of eddying regions like the Agulhas retroflexion region. And you can see in the temperature further down that there is some significant biases in the tropical Pacific at the thermocline depths. For salinity, there's in the Arctic, there's a significant bias in the Arctic where you've got a negative average increment at the surface and a positive one below. There's also a significant bias in the North Atlantic, the center of the North Atlantic, which is quite consistent with depth. And then there are some other biases in the tropics at the surface, particularly you get some positive average increments there. So how can you correct biases in using the data assimilation? Well, the Mercator system, I think, uses a bias correction scheme based on the average temperature and salinity innovations accumulated over the previous month or more, depending on the coverage, and applying a large-scale analysis to that data. Another approach is to estimate biases within the data assimilation, and in our case, we're using a variational scheme, so we can add terms to the variational cost function, which will estimate biases. And
Next slide, please.
An example here where you've got the SST biases, or sorry, observation biases in the C variable and model biases in the B. So for the observation biases here, we're trying to estimate biases in satellite data, particularly for different satellite SST data sets. And then we also include a bias correction, which is associated with the mean dynamic topography when we're assimilating the altimeter data. And if we can estimate biases in the model, then we can apply that when we run the model to correct it. What we currently do instead of that is we do a post-analysis estimation of the model biases on each cycle. So basically accumulating the increments of the state variables over the previous few months with some time decay associated with it on each cycle, and then combining that with an offline term of the bias, which can be estimated for the Argo period reanalysis. So that's good in the sense that it's simple to calculate the bias without doing any changes to the assimilation scheme. But there are some disadvantages. So we need to estimate an offline term, which basically means we need to do the reanalysis twice, or at least part of it. And then the characteristics of the bias are determined partly by the state error covariance matrix BX here. So it would be better probably to be able to specify the characteristics of the biases in the main analysis. And then there's work going on at Surfax and ECMWF to move in that direction, the NEMO. And we've heard a lot about machine learning as well, which can also help with estimating the biases. So now just a few examples of some specific issues with bias that we see in reanalyses. So this is an example in the equatorial region where the dynamical balances between the surface wind stress and the subsurface pressure gradients, and that gets disrupted when you're correcting the subsurface TNS fields through the data assimilation. So we've done some work for a long time on this regarding applying a bias pressure correction scheme. So there you can use the average TNS increments to adjust the horizontal pressure gradients near the equator, and that does help with this issue. We've recently revisited this and in the way it's applied in NEMO, and then improved the scheme to reduce changes to the pressure gradients in the deep ocean, and that's led to some quite significant improvements in the results. So on the plots on the right, you can see the innovation statistics for the profiles, temperature profiles, and sea surface height on the top there. And with this updated version of the scheme, you get significant reduction in the innovations. And then the bottom plots are showing the variability in the vertical velocities in the Western tropical Pacific as a function of depth and longitude. So you can see that a free-running model has quite low variability in the vertical velocities, but when we do the assimilation, we significantly increase the variability. And that's important because it can mess up the nutrients when you couple biogeochemical models to the system. With the updated scheme, we do reduce the variability in the vertical velocities and also the mean vertical velocities, which is not shown.
Matt,
yeah,
you hear me? We are still on the, I think, your second slide or third one.
Oh, really?
On how to use data assimilation. So,
can you see now? Is that?
Yeah, the equatorial bias, yes.
Okay, sorry, I don't know why it wasn't moving.
And we have 2 minutes left.
Okay.
Sorry. Go on.
I don't know why it's not updating. I'll try I'll stop sharing and share again. I'm sorry, I can't get it to move on slides.
Which number? Excuse me, Matt. We are sharing the slide for you.
Oh, you are sharing. Oh,
and we are in equatorial bias slide.
Yes, okay. So can we move to the next one then, please? Okay. Sorry. So I'll just give this example and then move to the end, then given the lack of time. But so this was just when we're doing SST assimilation. There's the plot at the top here is showing a cross section of the average increments in the Southern Ocean region for a month. And in this example, we're only doing SST assimilation. There's no profile assimilation, just to sort of mimic what happens when you don't have much data in this sort of region in the pre-Argo period. So you can see that there's a mean bias at the base of the mix layer in the increments. And that's because on average, the positive increments are projected deeper than negative increments. The way we do the assimilation of SST is to have a vertical length scale, which depends on the mixed layer depth in the background field. So we've been trying to investigate this a bit and have been running a 1D system. So in the plots on the bottom here, we're just looking at a 1D version of NEMO in an identical twin experiment. There's only SST observations assimilated and they have random error imposed. And the model is perfect in this identical twin case, and the surface forcing is perfect too. But using this method to do the vertical propagation, you can see that there's a bias in the resulting analyses. When the mixed layer starts shallowing in late spring, then the increments that are projected at the base of the mixed layer are on average slightly positive, and then after it's shallowed, there's no way that those can be corrected by the assimilation because we're not assimilating any profile data. So those biases persist throughout the rest of the summer until the mixed layer deepens again. And we've tried quite a few ways to solve this issue. So you can produce salinity. No, back on the previous slide, please. Still, but you can produce salinity compensating the density so that you don't change the density in the mixed layer, which does slightly improve this issue. But then you end up with worse salinity analyses. And so what we ended up doing is doing some time filtering of the mixed layer we're using to propagate the information in the vertical. And that does seem to reduce the issue, which is the plot shown on the bottom. But this is definitely an outstanding issue. We need to do more work to improve this issue. Okay, so perhaps we could just go to the final slide. I did want to show an example of high latitude assimilation of altimeter data, but we can just go to the next one because I think lack of time. So yeah, Mike's shown some ways to improve the model. Reducing biases is an ongoing process in the model for improving parameterizations and making the most of the resolution we have. But reanalysis definitely contain biases which are not due to the model, and they're probably dominated by those in some cases. So I've shown some examples of issues near the equator, this issue with the SST assimilation and the way it's propagated vertically. There's also an issue that are in the slides about high latitude assimilation of altimeter data. So I guess the things we should focus on is to continue to try and identify the causes of some of the biases we see in the reanalyses, and at the same time trying to improve the methodology we're using for bias correction and the assimilation itself. So moving to use machine learning perhaps, and implementing weak constraint algorithms to estimate the bias in a better way. And we could also use assimilate more observations where they're available. For instance, the salinity biases might be reduced by assimilating satellite SSS data, but those can introduce artificial trends in the reanalysis if you don't have the data going back into the historical period. So we need to be a bit careful about how we do that. So that was the end, and sorry for the technical problems.
Okay, thank you. Thanks a lot. Because we're out of time, I propose people have questions to post on Slido, and Matt and Mike, you can answer on it. It will be quicker. And thanks a lot, because I know it's complicated. We have asked 2 weeks ago to prepare something, and so thanks a lot on your side. And now we will switch to the next talk of this workshop. But last but not the least, because this is concerning the river input, this is done by Stefania. Okay, Stefania? Can you?
Good morning.
Good morning.
Okay, you hear me? First challenge.
Perfectly.
Perfect.
Perfectly. You
Second
can share
challenge.
your screen?
Yes, I'll try. Okay. Do you see my screen?
Yeah, screen. And now on presentation, not in presentation.
Okay. Ooh, no. Okay.
Okay, and slide your black square at the top on the other screen. Yeah, at the top and yeah.
Sorry, I didn't understand. Is it working or is there any?
No, you have still a black square at the top.
This is your Zoom navigation bar. Just slide to the other. Just slide it to the other screen. Your Zoom navigation.
I don't have I only have one screen.
So you can go like that. It should be okay.
Yeah. Okay, go like that.
Oh, now it's.
Yeah, now it's perfect.
Okay.
Yeah.
Okay. Let's hope it works this way. Thanks a lot for the introduction, and it's really a pleasure to provide a presentation about EFAS and GloFAS, which are two services of the Copernicus Emergency Management Service. Okay. So the Copernicus Emergency Management Service has actually 7 services in total: on-demand mapping, early warning and monitoring, and exposure mapping. This presentation will focus only on one of the services, which is the flood component of the early warning and monitoring. So this presentation will be probably quite different from all the presentation that you heard so far, because we are moving towards the land surface. First of all, I will explain what EFAS and GloFAS are, and then we'll provide an overview of the biggest change that we had to both the system over summer. EFAS and GloFAS have a lot of aspects in common and some differences. It's probably we can imagine them as siblings. So they are both early warning systems for flood monitoring and forecasting. So they provide information about upcoming and ongoing floods, and they are meant to provide information for medium to large catchments. Their purpose is to be complementary information compared to the national and regional services. And also they provide probabilistic information based on hydrological modeling and meteorological predictions. They also use in-situ measurements, and we use satellite data for implementation and for monitoring. We don't use satellite data at the moment in terms of data simulation. It's probably something that will come in the future. Let's move on a little bit more into the details. They provide medium range probabilistic flood forecast. EFAS, which is the European flood awareness system, provides information for floods upcoming in the next 10 days. And GloFAS has a longer lead time because we look here at the global flood awareness system, so catchments worldwide, which are larger than catchments in Europe, and we have a 30 days lead time. Then EFAS, the European system, also has post-process bias-corrected forecast using in-situ observation of discharge and flash flood indicators based also on radar flash flood nowcasting. For the European system, we provide notification twice a day to the EFAS partners, and the forecasts in real time are restricted to the EFAS partners. Everybody else can actually access the system and see the forecast with a 30-day after the 30 days embargo. For the global flood awareness system, we don't send out active notifications, but the information are available in real time. So everybody can access the global map viewer and retrieve information about the upcoming floods. We also provide seasonal outlook up to 4 months for both the systems. And despite both the system are, let's say, focusing more on discharge forecast, we also provide information about all the hydrological states of the catchments, including soil moisture, which is used by the complementary service of the of SAMS, which is the drought service. And also we provide snow maps, anomalies, and low flow indicators. We also provide impact forecast, and we collaborate with Copernicus Emergency Service Rapid Mapping to provide monitoring of flood events from using satellite images. Now, this was just a brief overview of the services. I will now dive into the major upgrades that we had over summer. Both the systems were upgraded. to a new version. EFAS was upgraded to version 5 on the 20th of September, not even 1 month ago. And GloFASv was upgraded to version 4, sorry, there is a typo, on July 26. The biggest change, probably the most visible change, is the increase of spatial resolution. EFAS used to have a resolution of 5 kilometers. The newest operational setup has a resolution of 1 arc-minute, that is roughly 1.3 kilometers. So we have a 16 times higher resolution. GloFASv used to have a resolution of 10 kilometers. It has now a resolution of 0.05 degrees, that is 5 kilometers. So we have a 4 times higher resolution. This is the most obvious and the most striking difference. But however, to achieve this change, we also improved a lot all the complementary parts of the system. We are using an upgraded version of Liege open source, which is the hydrological model that is at the core of the forecast. And we proceeded to a new calibration of both the system with an increased number of observed data. So first of all, I would like to explain why this change in both the system is so important and so relevant, and why do we expect a large impact on the results. I already mentioned that we have a higher resolution for both the system, and that, of course, allows us to better represent the spatial variability, the features of the catchments. So in terms of river network, for sure, and also soil properties, land cover, all the features that have large impact on the rainfall runoff answer of a catchment. But that's, as you can see in this slide, it's just one side of the story. Because while producing the setup at higher resolution, we actually also went back on and reviewed the methodology to produce each single map of the setup. The previous setup was produced roughly 10 years ago, meaning that now we could benefit of 10 years of research, technological development, and data collection. So we produced a setup that aims to better represent the physical properties of the catchments. We expect that this higher quality representation allows a higher quality and higher accuracy representation of rainfall runoff processes, which again leads to more accurate predictions and models of river flow, so the discharge estimates, but also of all the other states, for instance, soil moisture or snow cover, and so on. Just to make an example of this revamped setup, we had to reproduce over 100 maps, which are used within the modeling setup. And here we just provide 2 examples to highlight that we use a combination of sources. For instance, we needed to have the leaf area index, which provides information about the density of the canopy cover. And for this purpose, we used the Copernicus satellite-derived product, the leaf area index collection. And that allows us to basically have information on how canopy cover changes in space across the world, but also on time, because depending on the latitude, depending on the climate, leaf area index, the canopy cover changes depending on the season. Going to the opposite example, for instance, for the soil properties of the catchments, we used in-situ data, which were available from a database of over 200,000 soil profiles, soil samples provided by the open database Soil Grids. So these are just 2 examples to say that we really made an effort to provide the best possible representation of the physical properties of the catchments worldwide in order to have the best possible model implementation. If you are interested in reading of the details of each single map, we have documentation available online, and we actually also submitted a technical note, which is now open for discussion and until mid-October. I will try to remove this bit, probably I can't. Okay. What I wanted also to share in this presentation is that the complete set of maps, high resolution for both GloFASv, so for both the global domain and the European domain, are available for download. So you can go to the JRC data catalog and download the maps, and you can use them also for other purposes, or you can use it to implement the hydrological model, which is used also by EFAS and GloFAS. So the hydrological model, which is used for the flood awareness system, global and European, is called LISFLOOD. It is open source, so the code is available on GitHub, and it's also available on GitHub, a set of tools for the calibration and for the implementation of the model. Just to provide an overview of the hydrological modeling process, LISFLOOD includes 6 land cover fractions within one grid. So, and this is to maximize precision while achieving a good trade-off with computational efforts or computational costs. The 6 land covers are forest, irrigation, divided into traditional drained irrigation and flooded irrigation, sealed fraction to model the urban areas, and then we have open water and all the other land covers. We have then 3 soil layers, 2 groundwater storages, river routing in the river itself and also in the floodplain when the channel capacity is exceeded is the model using the kinematic wave approach. The model includes lakes and reservoirs, and we also include the impact of water abstraction for human purposes, for domestic use, industrial, livestock, and so on. One aspect that we did really have to focus on to be able to deliver GloFASv4 and EFASv5 was the computational efficiency. So to parallelize the computation as much as possible so that we could actually run this hydrological model at high resolution at global and European scale and operationally. So it means that we need to deliver the forecast on time to our users. And the calibration has been done using in-situ discharge measurements. So we use the distributed evolutionary algorithm for Python as a methodology and the clean Gupta efficiency as objective function. Of course, we didn't have discharge measurements everywhere across Europe or in the world. So we also implemented a regionalization approach for those areas for which we don't have measurements. But let's have a look now at the actual results, what you can actually now have in terms of operational model. EFAS version 5, we have here the map of all the points that were used for calibration. The calibration focuses on the year from 1990 to 2021. And the minimum calibrated area is now 150 square kilometers, as opposed to the previous 500 square kilometers. And we had almost 2,000 calibration points. I would like to highlight that in this map, the yellow points are all the points that were calibrated for the first time in this new release of EFAS. So quite a big number of new calibration points. The other aspects that I would like to highlight is that if we look at the figure here on the right of the slide, on the top, the purple red are the flood signal as seen in the previous model implementation, so in EFASv4. The image on the bottom right, which is unfortunately a bit covered by this, okay, now it's not covered anymore, actually shows the same forecast, so the same flood signal for the same area, but with EFASv5. So you can see that it's really much easier to see the distribution of the river network and actually to figure out the condition of each of the river network also for smaller catchments. And the improvements of EFASv5 were also actually quantified by producing the distribution, the empirical distribution of the KGE values for calibration. Here we have in blue, it's the performance of EFASv4, previous model implementation. In red, the performance of the new model implementation. We have a shift towards the left of these curves, and that means that the performance of the model overall improved. But if we focus only on the small catchments, so if we focus on the catchments with drainage areas between 150 and 500 square kilometers, we see that the red line is much more closer to the right compared to the blue line. So it's really for smaller catchment that we had a better, higher performance. We have this information is actually provided in the EFAS map viewer. So there is a map that shows for each catchment the KG value in calibration. And if you click on each one of the calibrated points, you will have these diagrams that we call speedometer, where you can see the KG value, but also its three components, so bias, variability, and correlation. And this is available for all the points in the EFAS website. And also we have documentation where we explain the performance and also how we selected the calibration points and all the details. Similarly, we can discuss the results for GloFASv4. Here in this map on the left, we can first of all observe two colors. The blue one includes all the areas in blue were actually calibrated for GloFASv4. The yellow one are the areas which we couldn't calibrate because we didn't have data. And I will explain in a minute what we did in these areas. But for now, let's focus on the blue areas, because I would like to highlight that we have two sets of points, the black points and the red points. The red points were the points or the gauge stations that were calibrated for the first time in GloFASv4. And that means that we really had a much larger number of calibration points in Africa and also across all the continents. And this is thanks to improved collaborations with researchers and local authorities all over the world. And I have to say that GloFASv4 can benefit of 700 more calibration points compared to the previous version. And this, of course, has a huge impact on the performance of the model, which can be summarized here on the right, where in black we have the performance of the previous version, and in red we have the performance of GloFASv4. The thick line shows all the stations, and we have a consistent shift on the right, thanks to the improved model setup with all the new developments with new data, but also thanks to the larger number of calibration points. If we look at only the points that were calibrated in both the system, we have this dashed line, and we still see that the red line is much more on the right compared to the black line. So the improved performance of GloFASv4 compared to the previous system is stemming from a combination of factors: better model setup, higher resolution, and also larger number of calibration points. Again, we have a open source page where we explain all the details of the calibration. And similarly to the European system, in the GloFAS map viewer, you can retrieve for each calibration point the speedometer, which shows the components of the KG, so correlation, bias, and variability. To differentiate a bit compared to the slide on the EFASv5, I have here the map of the KG values for the global domain for each calibration point. And we can say that any point which is from orange to blue has good KG values. Unfortunately, we still have some black points and where the model performance is not satisfactory. And this is largely due to large bias. You will, if you have the patience to explore the wiki page, you will see that in fact, in GloFASv4, we were able to remove or to reduce a lot the bias in many stations worldwide. But still, we have some issues, especially here in Africa, along the Nile or in Sudan. If we look at the improvement, as I said, the bias was probably the factor that we improved the most. We had a smaller improvement in correlation and variability compared to the previous version, but still an improvement. And finally, just a few words on what we did in all the yellow area where we didn't have observations to perform the calibration. We decided to use a parameter regionalization approach, which means that we decided to transfer the parameter set from a calibrated catchment, which we called donor, to a not calibrated catchment. We identified over 700 donors around the world, which are the black areas here in this map. And we use them to transfer the parameter set to one of the catchment in the yellow area. The question, for instance, if we have here a catchment in China is, okay, but what is the donor? What is the appropriate donor? The closest one, the most similar according to what? We did a cross-validation experiment, and we identified that the best way to identify the donors was to look at spatial proximity, but also at physical proximity, especially looking at climate. So we implemented this regionalization approach based on geographical proximity, but also on physical proximity, and we used the regionalized parameter map to set up the operational GloFASv. So the very last 2 slides, I really would like to stress that now both the systems are being upgraded and they are both operational. For us, it was a huge change and a huge challenge, I would say, over summer. And the very last slide I would like to share with you is the data sets that are already available for download from the Copernicus Climate Data Store or from the GRC data catalog. In terms of reanalysis, the discharge reanalysis for EFASv5 and GloFASv4 are both already available from the Copernicus data store, and we also provide a user guide in order to help to download the data and to use the data in case you want to do some analysis on the data or to better understand what you find in the files. So for EFAS, it goes from 92 until near real time and with 6 hours frequency. For GloFASv from 1980 until near real time, and they are of course constantly updated, and it has daily frequency. We're talking about discharge, which is already available. In the near future, we will also make available soil moisture index and snow water content. On the CDS, you also find the medium range forecast in real time for GloFASv. We've offered the 30 days embargo for EFAS, and this is due to the one voice principle, which is in place in Europe. The seasonal forecast and the medium range and seasonal reforecast are already available for GloFASv. They will be delivered soon for EFAS, soon meaning by the end of the year, or anyway in the next few months. And one data set that I haven't mentioned in this presentation, which is the flood hazard map. Basically, they show the flood extent with different return periods, with 90-meter resolution, both for the European domain forced by EFASv5 and for the global domain forced by GloFASv4. They will also be available in the next few months from the GRC data catalog. I've already mentioned that these flood hydrological model implementation maps are already available from the GRC data catalog. And with this slide, which is probably the most interesting, because it finally shows that everything is available and everything can be used, and everything is open for feedback, because we are always trying to improve the system. So, of course, there will be EFAS6 and GloFASv5 based accounting for the feedback from the users. So I encourage everybody to provide the feedback, or if they use spot errors, please let us know.
Okay, thanks a lot, Stefania, for this very nice talk. Maybe one quick question or comment. Yes, Lotfi.
Thank you for your talk. Do you have any plan to use swath altimetry data for the hydrology from for your system? Or?
Yeah, especially this question actually connects very nicely with the question that I have here in the chat. We had some talks, not plans yet, so talks and interesting discussion to see if we can eventually use SWOT for reservoir, to monitor the reservoir level. At the moment, it's scientific talks. We are trying to figure out if that's possible, and it's an ongoing discussion. So to go back, probably that I hope this replies to your question. So yes, at the moment, mainly for reservoirs, because reservoir, as highlighted in the chat, are one challenging feature whenever you have to include them in a model. What we use now, it's data provided from the partners in terms of reservoir storage and physical features. We don't have any data simulation of real-time data. And the challenge is that in the model, we use a set of precompiled operational rules, which are the same for all the reservoirs worldwide. And that means that sometimes the forecast of discharge downstream of a reservoir, it's really hard to do, because if you don't know what the reservoir manager is doing, you will never be able to set it up in your model. One option is to use satellite altimetry to actually do data simulation. You know how full is the reservoir, and then the model can react according to the level of fillness of the reservoir.
Okay, thank you. And last question from Emanuela on Slido. Do we have some plan for extend EFAS before 1992?
For the reanalysis, no, we can't, because the reanalysis is based on observed meteorological forcings. And we have a database that extends back to 1990. The reanalysis discharge is available from 92 because we need at least 2 years of warm up or spin up of the model. So going backwards at the moment, it's not really foreseen because we don't have meteorological observation with such a large coverage, pan-European coverage before 1990.
Okay.
But the GloFASv1 is based on the ERA5 reanalysis. So at the moment, it's from 1980. We know that ERA5 is now available from, I think, 1950. So in that case, for GloFASv5,
1940, exactly.
1940, okay, even better. Yeah, the challenge there will be to have calibration data. But basically when we release we finished the reanalysis of GloFAS, the ERA5 was extended backwards, and that's when we said, okay, next time we really need to use the full data set. Unfortunately, when we started working on GloFAS4, the data set started from 79. But definitely in that case, we already discussed extended backwards.
For the next release, it will be perfect. Thanks a lot again, Stefania. And I think this is the end of this session. Now we have a wrap up, but we are very late. So, Marie, you want to say something?
Yes, we can say something. First, we want to thank all the speakers, today's speakers, and all the speakers of the workshop again. Thank you very much for coming or for being online, for those of you who are online. So we can see you now on screen. Thank you. And do you want maybe to add something?
Yeah, thank you very much, really, particularly people from long way to come. I think we will not give you any summary today, but we will sum up all the presentations, questions, and we may share with you a report or something like this. Even we will see, maybe even a white paper, something.
Yeah. And we will send an email to speakers and presenters of posters if you agree to share the PDF versions of your talks. We will put them online. So you can just write me an email if you don't agree, but I will send I will confirm later by email. And
also, if you want to put your contact email address on your presentation, would be good as well, because people ask for your contact information.
Yeah.
I think everybody more or less okay to try to work together. So I think we should find something, a way to synthesize how we can do. to be more efficient. And so for that, we will try to summarize as best as possible the different sessions with the help of the chair and to disseminate after the conclusion. And we realize that there is different reanalysis type. There is the coupling possibility or not. There is domain, etc. So we should clarify some point to do something very clear. And it's the first workshop we have done on this topic, so we have tried to manage and to give the floor and the audience at every component. If you have some remarks, some proposition for improvement or in the future or whatever, don't hesitate to contact us, and we will do our possible to do something better in the future, maybe. And thanks a lot to everyone.
Thank you. And thanks also to our scientific organizing committee and to Copernicus Marine Service also, of course, Pierre-Yves, for making this possible. Yeah. Thank you.
And from people here, there is a small lunch.
There, yeah, you can go downstairs for lunch. And also, thank you, Vincent, again. And thank you to the Artilect people for hosting us.
Yes, actually, I think we owe a round of applause for the local organizing people who put in a huge amount of work on this.
So thank you, online people. See you soon. Thank you, speakers. Bye-bye.
Bye.
And for on-site people,